오늘 시작하기 전에 잠깐 저희 인터내셔널 세미나 설명을 조금 드리고 시작을 할게요. 약간 시간이 늦어지긴 했는데 일단은 이번 세미나 같은 경우는 저희 스마트시티 엔지니어링 저희 학교에 있는 프로그램이 있어요. 거기 이제 BK21 프로그램 하고 있는 학과가 있는데 그 학과랑 한국도로학회 그리고 마지막으로 이제 저희 교통물류공학과에서 공동으로 좀 주최를 했고요. 이번 세미나 같은 경우는 실은 국제 세미나 형태로 해서 저희 이제 정현 교수님을 모시고 좀 강연을 듣고자 하고자 하고 있는데 아무래도 이제 여러분들 대부분 학부생들이나 또 대학원생들 좀 학생들이다 보니까 제가 특별히 요청을 드려서 행사 진행이랑 다른 분들의 어떤 발표는 한국말로 하되 저 아티 교수님의 강연을 영어로 진행하는 걸로 이렇게 했거든요. 그래서 잘 들어주시면 좋을 것 같고 제가 시작 전에 일단은 조금 소개를 좀 드리려고 합니다. 그래서 일단은 if you don't mind, just stand up. I want to introduce you. 박수 좀 모셔주세요. 유니버시티 오브 센트럴 플로리다의 모하메드 압델라티 교수님이시고요. 여기 보시면은 제가 좀 설명을 써놨는데 실은 교통 안전을 연구하시는 분들 중에서는 뭐 단연 탑 리서처라고 할 수 있을 정도로 굉장히 많은 실적을 가지고 계시고 또 제자들도 많고 되게 저명한 교수님이십니다. 그래서 여러분들 앞에 이렇게 좀 소개를 시켜드리고 싶었고 특히나 교통 안전 쪽 저널 중에 Accident Analysis and Prevention이라는 저널이 있어요. 거의 이제 세이프티에서는 가장 탑 저널인데 여기 이제 에디터인 치프를 10년 이상 하셨습니다. 그래서 되게 유례 없는 일이고요. 10년 이상 그렇게 전화한다는 게. 그리고 그 클레버베이트에서 2020에서 2022년 사이에 얼마나 많은 사이테이션이 됐는지 연구자의 어떤 그 실적은 논문 참조가 얼마나 많이 됐는지에 대해서 좀 좌지우지가 되는데 전 세계적으로 0.1%에 드셔가지고 여기서도 주목을 받으셨고 그리고 연구 분야는 아마 이제 발표를 좀 해주시겠지만 교통 안전 그리고 그 안에서 이제 스마트시티 어떤 어플리케이션들이랑 이런 것들을 많이 하십니다. 그래서 좀 설명을 드리면 좋을 것 같고 그다음으로 두 번째 발표는 이제 저희 이제 교통물류공학과에 작년에 새로 오신 김성후 교수님께서 좀 재밌는 연구를 소개해 주실 텐데요. 김성후 교수님 잠깐만 일어나시면 제가 여기 김성후 교수님. 저희 과에는 작년에 오셨고 교통 계획 쪽 연구에서 제일 단연코 현재 주니어 레벨에서는 제일 훌륭하신 분이라고 보시면 될 것 같습니다. 이따가 또 발표를 해주실 것 같고요. 그리고 두 번째 이제 스피치에서는 그 서울대학교에 지금 연구원으로 포스트학 연구원으로 계시는 주양준 박사님이 발표를 해주시겠고요. 잠깐 일어나시고 있어요. 인사하세요. 주양준 박사님. 두 번째 세션은 실은 약간 영 리서처 세션으로 해서 이제 막 학위를 받으신 주양준 박사님이랑 학위 과정에 있는 저희 학생이 이제 발표를 해주실 텐데 잘 들어주시면 좋을 것 같습니다. 네, 그리고 패널은 제가 이따가 다시 설명을 드릴게요. 그래서 우선 발표는 저희 이제 모하메드 압델라티 교수님 모실 건데 제가 플로우로 모시면 큰 박수 좀 부탁드리겠습니다. 압델라티 교수님이십니다.
안녕하세요. So I speak Korean, but I'm not going to speak today. So thank you for attending my presentation. It's a pleasure to be back here in Hanyang. This is my third time I come here. Also, I have one of your colleagues who is a PhD student with me now from Hanyang. So our relationship has been very useful and productive. And of course, Professor Jun Yang is a graduate of my department also. So I prepared two presentations. I didn't know which one, and then I asked Professor Park. I said, both, why not? So I hope it's useful to you. So the first one, I want to talk a little bit about some of the research that we have, and just give you a flavor. Maybe I'm not going to go deeper into any special topic, but I'm going to give you kind of an overview of what are the direction of research that we are moving on. I think our field of transportation is evolving very quickly. It's changing. There are a lot of new ideas, and really a lot of engineers are working in transportation, even if they are not strictly transportation engineers or civil engineers. We have a lot of electrical engineers, computer scientists, automotive engineers, because there are a lot of opportunities, a lot of ideas, and everybody wants to be involved in transportation. So that's a good time for us as transportation engineers, but also it's a challenging time because we have to understand a lot of new things. So I want to today touch on a few important subtopics such as AI, big data, real-time applications, computer vision applications. I want to talk a little bit about simulation and what we can do, simulation or digital twinning, which is beyond simulation. And also a concept that we came up with at my university, my team, several years ago, the concept of proactive traffic management. You all maybe hear about what's active traffic management, but I want to talk a little bit more about proactive traffic management. So, what did I do? All right. So what we have now is a lot of new data types that we are using. Maybe the first circle has some of the now we can consider traditional data, not very new but still different, which are such as probe vehicles, for example, GPS data, what we call ITS data, such as sensors data, etc., weather data. These are being used more and more in transportation, but I also want to draw your attention to a new type of data sources such as videos or images or data coming from smartphones or LiDAR data. You all, of course, use a smartphone. You know that your smartphone has 7 or 8 sensors. Right? You know that, right? So imagine all of us, we are collecting the data that we are using while we are traveling as pedestrians or vehicles. This is huge data that we can use. So I prepared a chart from one of my recent work that has all the data that we are using in my lab. And I'm sure you are using a lot of these data. So there are a lot of traditional type of data on the left side, which are infrastructure, accidents, conflict, violations, geographic data, etc. But look at the right side, you're going to find more of new types of data, such as microwave detection, such as AVI, automatic vehicle identification data, Bluetooth detectors. ATSPM data is a signal operation data that we are getting live also. So every time the signal change, we are getting this indication in my lab automatically. All this data are real time, and we are capturing it in real time in our lab. So we have fiber optics with the Department of Transportation. So all this data is being collected in real time and fed into our lab. We have also been using the transit data. So all the buses, they have GPS. We are getting this data, location data. From GPS, you can determine speed, for example, acceleration. There are also new types of data such as Waze, Letex, Strava, Twitter. You know Twitter, of course. So these are either new apps on the phone or social media type data that we are also using, because social media, if you screen for the data related to transportation, you can get also more information about how people are traveling and thinking, right? So all this data we are capturing. Waze is a connected vehicle data. I'm not sure if you know about it. It's a UK-based company that has an agreement with vehicle companies. And you know that many vehicle companies now track everything in real time. It's sent to the company. So you're driving, for example, a Ford vehicle. Your steering, your braking, your wipers, your light, your acceleration, everything is being sent live to the company. The company assemble all this data and then sell it. Waze buy it and then sell it to us, right? So therefore, this is connected vehicle data, because this is live data of the, it's not really connected vehicles, but it is giving you very close to connected vehicle data. So you can use this in many applications like modeling acceleration, modeling conflicts, modeling behavior. We use it in a lot of applications. So anyway, I'm not going to go over all this data, but now imagine you have all this data in your lab and you're getting stream of this data. What do you do? I mean, so this is very valuable, right? It's very precious. But the challenge is, okay, so what do we do with it? I mean, there are a lot of things that we can do, right? So now AI becomes a very important, because it helps us to either use this data for prediction or processing this data to get items that we need in our research, right? Whatever your research topic is. So we talked about a lot of data sources, and then we can process it. So AI can help us to process the data. And then after we process the data, AI or machine learning or deep learning can help us use these data for prediction, right? So there is a component of using the data to process the data, and machine learning is very important. And there's a component that we use machine learning to predict using this data. So this is an example of how to use machine learning to process data. So this particular example, everything I present here is a study in my lab. So these are real projects that we really use. So this picture shows you the area in Central Florida where I live and where my university is. And all the orange shapes are where the weather systems are. So you get an indication of what is the weather, precipitation, fog, etc. And all the blue dots are the CCTV cameras on the road. Right? So you see that we have a very dense network of CCTV cameras. And what we did is basically, we found that these weather stations are not very useful for us because they are not necessarily close to the road. And the spacing is very wide. So you cannot get continuous coverage. So what we said, okay, we're gonna now use these cameras and process the images or train the model based on these images to identify the visibility, identify the pavement condition. Right? So now once we train this model could be applied in real time, and the camera, which is designed for traffic, is not designed for weather, will detect the image, and the algorithm or the machine learning will tell us what is the weather condition, heavy rain, light rain, and what is the pavement condition, wet or not wet, etc. Now, this information is collected with the help of machine learning and computer vision, but it's very valuable for transportation, right? Because we know that the traffic changes based on the weather condition, and safety also changes based on the weather condition, right? So therefore, now we have free, basically, source of data, right? Because these cameras are there anyway. So this is an example of how we use machine learning for prediction. This is also a project that we're designing a smart corridor, and the smartphone was the main source of our data. And so we collect from the smartphone the position, the accelerometer, the magnetometer, and all the parameters that we collect from the smartphone, and then we process this data to give us the probability of people driving in certain, like turning right, going through, doing a U-turn. So we model using machine learning the speed and the turning movement of vehicles. Now, why turning movement is important in a connected vehicle environment, you need to know that, right? Because if there is a pedestrian crossing or there is a possibility of an accident and the driver is turning with high speed, you need to warn. And this is the connected vehicle concept, right? So we can use smartphones actually to generate the data that we need for connected. So this was part of the smart corridor study. So you can see that what we used, I'm going to just talk about the interesting parts, right? So we are using here sound, camera, LiDAR, UWB, Wi-Fi. UWB, now you have it on your smartphone. You have a UWB, but it's not open yet. You know what's UWB? It's a sensor. You know, Apple, when they created this pod so that you can track your bag, for example. So you put it in your luggage, and then with the smartphone, you know where your luggage as you travel, for example, right? So this is a UWB, but it's not open. But you can buy UWB system outside the smartphone. But soon it's going to be open on the smartphone. So we use it to track pedestrians crossing an intersection. So, but the interesting part is that we use sound also. Have you ever thought of using a microphone in traffic to detect events in traffic? So actually we have a paper about this. So there are certain sounds that you can detect with a microphone and machine learning, of course, to determine what's happening. Is it an accident? Is it a braking? Is it a siren from an ambulance? Only using sound. So as you can use cameras in traffic studies, you can even use sound in traffic studies. And police now use this all the time. You know that, right? So we have, for example, microphones in downtown Orlando. And if there is a gunshot, because, you know, America, of course, we use guns a lot, right? So if there is a gunshot, the microphone will detect the sound and will alert the police. So sound is also important. So anyway, so we use this to achieve, you know, the detection, prediction, prevention, etc. And we can achieve all this with these sensors, right? We can influence the signal timing, account of vehicles, what are kind of events you are experiencing on the road, what is the speed. We can visualize what's happening, like this picture, for example, is visualizing where there is a conflict between a bicycle and a vehicle. We can issue warning using infrastructure to pedestrian or infrastructure to vehicle. So the camera is the infrastructure, right? And the camera is detecting a pedestrian or a vehicle and then sending this information. And then share all this type of data for different applications. So I want to talk a little bit about video, because this is one of the things that actually my team has been progressing in very fast. So there are a lot of things that you can achieve with a camera, video processing. You can achieve a lot of things in traffic. And I think I saw something here, right? You're doing something also related to video. So first we need to detect. We need to detect the object, whether it's a pedestrian, a vehicle, a large vehicle, a small vehicle, whatever. And we need to track it. And by tracking it, we get these trajectories. And these trajectories we use in so many applications. I'm going to talk about it. And then you get out of it all this traffic data and more, right? You can get speed, you can get conflicts or near misses, you can get behavior of drivers, you can get behavior of pedestrians, you can get conflicts between pedestrians and drivers, you can get a lot of traffic parameters by processing these videos, which become very useful in our analysis. And then now also when you look at the detection, there are different ways of doing detection, and we are kind of working in that two-stage detection using Google Images. You know that Google you can get a lot of images, right? So you don't only get the Google Earth, but if you go to Google Earth, you can see also images, a lot of images for every road. And these images help you analyze the infrastructure and also the environment of driving on the road itself. Actually, when you put the images together, you get like a video of the roads, all roads, right? So this is a very good source also of data. And the 3D pose detection is also very important in safety studies, because we start to deal with the object not as a box, but as a human. So you see a lot in video recognition, you see these boxes, right? The box is moving, but actually that's good to count, but it's not good to determine the near miss between a pedestrian and a vehicle. You need to see where is the arm of the pedestrian, is the pedestrian crossing the road, pressing the call button, where the pedestrian is looking. So this is important in modeling pedestrian behavior, particularly in safety studies. So you need to do the 3D pose estimation of pedestrians. So this is software that we developed called ARSYS. And ARSYS stands for something that I don't remember, automatic, whatever, conflict something. And basically, we created a very large data set of drone videos that we analyzed, about 1,500 minutes of drone videos at many locations. So all type of locations you can imagine, roundabouts, intersection, interchanges, weaving areas, all the interesting parts of the roadway network. We flew drones and sometimes multiple drones, and then we use these videos to process using our software. So our software is basically, you feed the video, and the software will determine all the statistics as well as the safety indicators. So if you're familiar with safety conflicts, what we call PET or TTC, time to collision, these are indicators of safety that we can get from conflict. So if you have the vehicle trajectories, it's kind of, you see where the trajectories come very close. This is a potential accident. Because if you want to wait for accidents and observe an accident, you'll be waiting for a year, right, to see an accident. But you can observe a lot of conflicts. And if we assume that conflicts are related to accidents, you can model safety also. So I think it's probably.
Maybe wait.
I need to wait. Yeah, I pressed several times, so I hope it's not going to change.
The file is too heavy, so.
Yeah, the file is large.
Oh.
Okay, so this is the software basically. So we do a lot of steps in order to use this software. So this one is a really sophisticated software, and we have the ability. When you fly a drone, the drone is moving, right? So you have to stabilize the video, right? Because the drone with the wind sometimes is moving. So this is the first step, and then we have the ability also to stitch videos from many drones so that you have a long segment that you want to study. And then we obtain the trajectories and all the statistics, and then we use that for data visualization and calculating of the TTC, etc. So it's a very, and then also we have active learning to improve so that the system is improving as it runs more and more. This is some of the locations that we analyzed using these videos, and you can see these are all now papers. And I can tell you that the first one is approach to Toll Plaza in Nanjing, China. And the second one is the approach to, I think, a tunnel in Hong Kong. You are familiar with this place? Really? It's your advisor, right?
Yeah.
So SZ, Tony Z is her advisor, who is a co-author on this paper. And then this is intersection in Florida. And I think this is an intersection also and a bike lane in Florida. And then this is a weaving section in China. I don't know, I think in Chengdu. And these are three. So in order to cover the whole weaving area, we have to fly 3 drones and then look at the whole video. So these are all conflict analysis that we use using this system that I just mentioned. And then here you can see, for example, the relationship between accidents and the relationship between the trajectories. This is just for illustration, it's not very important. And then here, a sample of the locations that I was telling you about. And by the way, this data, we opened it. So it's online. If you are interested to study any of these locations and get the trajectories, we can provide you these trajectories. So we first used it, tested, etc. Then we opened it for researchers. So far, there are about 100 university research institutes, vehicle companies that are using this data set. So this is a resource available for you. And not only the trajectories, but we also, as you can see, for every location, we created the digital map or the digital file for the location in 3 dimensions. So you can also drive this location in a driving simulation. So not only you can drive, you can analyze the real trajectories in the real world, but you can do a digital twinning study using the digital maps and even drive the location so that you want to test, say, an improvement or a new system or connected vehicle or whatever for the same location. This is also we provided in our data. So here are example of the digital map for the locations that I was talking about. So every location you can download the trajectories, you can download the digital map, then you can use it for whatever studies you want to. Another system that we developed is using the roadside cameras, and not only the roadside cameras, but the CCTV cameras. So you know that many of the video systems, you install cameras on the side of the road, and these are usually high resolution specialized cameras. I'm not very interested in that because these are expensive systems. But I'm interested in the CCTV cameras, which the government is already providing for traffic management. How can we use them? Because these are free, right? How can we use them to improve our applications in transportation? So to give you an idea, in Florida, we have 18,000 cameras on the road. So as if you have 18,000 people looking 24/7 on the road. And the machine learning is the brain, right? So you're thinking, you're looking, you can do everything, right? You can capture everything you want, right? So this is where we are heading. So here we are using the roadside cameras or the CCTV cameras too. They have problems. I'm not saying they are perfect. They have problems, but anyway, let's not talk about problems. What I want you to notice is look at the bounding box and look how tight the bounding box around the car. Most of the systems, because we evaluated the market, by the way. One of the jobs that DOT asked us, okay, many companies are coming and claiming they have a very good video system. Tell us, who's saying the truth, who's not saying the truth. So we evaluated the whole market. And most of them, you find this big bounding box that is kind of funny around the object. None is as tight as this. So our bounding box is actually not only around the car, but it's also rotating with the car, which is not in the current system. The other very important, here is the 3-dimension I was talking to you about. Because when you look at safety, you're not interested in the trajectory of the center of the car. Because the trajectories in all the systems available is the center of the car. The center of the car is good to count how many cars. But if you are looking at 2 cars coming close and having a near miss, you need the edge of the car. So the database I was talking about does not give you only one trajectory. It gives you 6 trajectories. The corners of the car and the front and the side of the car. So therefore you can model safety when the front of this car come near the side of this car. You can model this and not the center to the center because it will not be a problem, right? So this is a very important aspect that we are the only ones that did it. All the systems in the market that claim they evaluate safety, they look at the center of the cars. Very wrong, right? Very different, right? So anyway, so this is another software that we developed. And here you can see one of the examples of how we can do more safety evaluation efficiently. So if you are familiar, if you work with safety and you have a problem, right? So you discovered, there is an intersection that has a lot of accidents, right? And then, you report, to the government, or the government notice that statistics and say, okay, this intersection has a problem because, over the last 3 years, we have been having more than 50 accidents per year, and maybe few people were hurt. Okay, so this is the first step, right? So after 3 to 5 years, you discover there is a problem. You bring a company, consultant, and the company do a study and take a lot of money, and then tell the government, okay, now you need to change that, right? So change that, pay us more, and then we have to wait another 2-3 years to look at whether the accidents went down or not, right? This is what's called a before and after study. Very typical in safety, right? But guess what? How many years did you wait, and how many people got hurt before you concluded whether the problem is solved or not, right? So this is very inefficient. And with a lot of intersections, a lot of drivers, a lot of problems, you cannot keep up. You cannot spend all the money at all the intersections, right? It's impossible. Okay? So here what we are suggesting, we either fly a drone or we look at the CCTV, and using machine learning and computer vision, we determine what is the problem. So fly 2 days, 3 days, 1 week, right? And collect these videos, processing it with our software. And then, for example, here we are showing these red dots are where a lot of bicycles or pedestrians coming very close to the vehicles. There is a problem, right? There is a pedestrian problem, right? It's very clear. And the solution is very easy, right? So in the US, you are allowed to turn right when it's red, unless you prohibit it. So prohibit the right turn of the vehicles, because the right turn of the vehicles come with the pedestrian or the bicycles. So if you prohibit it, you remove this conflict. And then you fly the drone another couple of days, problem is gone. So in 2 weeks, you achieve what we used to do in 5, 6, 7 years. Very low cost, right? So this is an efficient way to do safety evaluation. Another is to use the cameras to help the autonomous cars. So as you can see, the autonomous car on the top, these are all the sensors, right? You see this picture a lot, right? So the autonomous car is moving, all the lidars, cameras covering all this area. You can see all these shapes are basically what the car is seeing around it. Okay. How about if this car intends to turn right, and there is a pedestrian now at the corner crossing the road? The car cannot detect that. But the camera on the road showing all this green area, can see all this green area. So what is the solution is that the camera detects the pedestrian. Using connected vehicles, this information goes to the autonomous car. So the autonomous car knows that there is a pedestrian around the corner, which means autonomous cars by themselves cannot operate in all situations. But we need the help from the infrastructure, and the camera will be that help. Right? So another example here, pedestrian is walking between cars, and this information is detected using the camera. The information is sent to the car. The driver detects the pedestrian and therefore react accordingly. You know who's the pedestrian, John Young, right?
Yeah.
You know who's the driver?
I know.
Okay. These are two of my students. And this is the Tesla. So the Tesla cannot detect the pedestrian because it's between the cars. Some examples of the work that we did for pedestrian modeling using machine learning. So pedestrian at which location we are, is risky for the pedestrians. The camera detects, and not only the camera detect, but now we are starting to predict. So see, I told you the pose estimation, right? So the pedestrian now is not a box. The pedestrian is a human. You can see the human arms pressing the button to cross, the people are waiting, where they are looking. All this we model in order to predict what the pedestrian is going to do. Because if the pedestrian is going to violate, this information needs to be sent using P2V, pedestrian to vehicle connection, so that the vehicle knows that there is a pedestrian about to violate before the pedestrian violates, right? So all this we can model. This is some of the models. All of them are machine learning type models. In this particular case, for example, random forest was the most accurate. But see, I mean, accuracy about 90%, pretty impressive to model pedestrian behavior. Machine learning and video allow you to do that. Okay, I'm going to shift now to simulation a little bit, just to give you a flavor of what we do in simulation. So we have this multi-driving simulation. By the way, we didn't buy this. We built all this software, hardware. We put the hardware together, and we built the software. And we have these 3 connected simulators. So what does these simulators help us? Help us model a connected vehicle environment. So these 3 drivers will be operating and connected at the same time. So they are interacting to each other behavior, right? So they are the drivers. But we connected this simulator to number 1, SUMO, which is a microscopic traffic simulator. We connected it also to 2 very important visualization and animation systems. The first using Unity, and we modeled this, and the second using Carla. I'm not sure if you are familiar with Carla, but Carla is a simulator that is built to simulate sensors in a connected and autonomous environment. So you can also simulate the sensors and simulate the connected vehicle type applications. Right? So basically, 3 drivers are connected to each other. At the same time, the micro simulation is running and generating vehicles that are appearing in their scene, and they are driving scenarios. So remember when I told you about the open data set and the digital maps for the different locations? We can drive them now because we are modeling this using Unity. So of course, there's a lot of connections between the systems, and what I'm not showing here is that all the system is connected to a cave, a room, where we are simulating. It's in a different lab, not my lab, where we're simulating the pedestrian. So the pedestrian is walking in this cave, and the driver here is seeing the pedestrian, say, crossing the road or approaching the vehicle, and the pedestrian is seeing the vehicle in this lab approaching, right? So pedestrian in the loop simulator is also doable with this system. And this helps us to create what's called digital twinning, right? So you are basically representing reality in the digital world, and then you take something from the digital world and then implement it in the real world. So this connection between the digital and the real world is basically the digital twinning that we are talking about. Some animations here to show you Unity platform, Carla platform. Again, the 3 connected simulators. These are all students in my lab. These are the digital twinning that I was talking to you about. And you can see the digital and the real image. The Google map and our digital map. You can see how refined and accurate the representation. So it's really realistic. And then we are using SUMO to generate the traffic that the driving simulator you are driving in the traffic. And by the way, a side note, we don't use traditional calibration and validation anymore for traffic simulation. So the concept of count the number of vehicles, we are using actually the drone trajectories to calibrate the micro simulation, so that it is a vehicle by vehicle calibration and not the number of cars in 15 minutes and all this. So it's very accurate calibration of our SUMO model. Some examples to show you all views of the same. So this is what I was telling you about the drone video. The same location, in Sumo, the same location in Karla, the same location in a driving view. This is all the same thing, by the way, but in different applications. Can you advance it from your side? Yeah, and this is also just to give you an idea the difference between Unity and Karla, how it looks, the difference between. And then, of course, we use this for many studies. I want to go one back. Right. So this is, for example, studying a non-controlled intersection, and we want to optimize the capacity of this intersection. So you can see, some of the applications we use the simulation I was telling you about. So here, for example, looking at the percentage market penetration of the different types of cars. So you can have a human-driven car, you can have only connected car, you can have connected and automated car, and the percentage differ in traffic. So what is the best combination to achieve the best safety and the best capacity for intersection? What is the best merging algorithm, for example? So all these testing, we can easily do it in this system that I'm talking about. And this is from a paper comparing the different. And then finally, I want to talk a little bit about now the data analytics side. We talked about big data, etc. So this is an award-winning system that we developed for prediction of accidents, or prediction of increased potential of accidents in real time. So basically what we are doing is something that in my lab we have been working on for the last 20 years. How can you predict in the next 5+ minutes if there is a high potential of an accident? So how do you do that, right? So we know that we're getting all this data, right, in real time. Now, if this type of data we related to historical accidents, we know what is the condition that preceded historical accident. So in the future, this type of algorithm will tell us if in the next 5-10 minutes there is a higher potential of an accident, right? So of course, it's not as simple as that. It's a long story, but just the idea, right? So now, every type of location in our network is different. You cannot model an intersection like a freeway, like a weaving section, like, they are different. So therefore, what's happening here is in the background, there are multiple machine learning algorithms and the data is being fed live to this algorithm. And the algorithm is giving us an indication of the potential of accidents, which is represented in color in front of you, right? So all this is in the background. This is the user will see this map, and this map is updating every minute. Right? So now you can look, of course, the colors represent the degree of risk, right? So, red means there's a problem expected to happen here in 5+ minutes. So anyway, so this system is actually running right now. I mean, this is again an award-winning system, national level. And this is running now in Florida, and we are expanding it. And it's giving you a lot of statistics about the network. And you can zoom at any location, say this red location can give you, now these are the top locations that need attention. And then it can give you, if you zoom at the location and click on it, it's going to give you the different, what's happening at this location, what is the volume, what is the speed, what is the variance in speed. And then, a traffic operation can assess what needs to be done in real time. And also you can click on the camera and see what's happening. You can also get a weather indication. You can also get a suggestion of what is the solution that you need to do now to prevent this accident or reduce its effect after 5-10 minutes, right? So in this particular example, a combination of ramp metering and reducing the speed limit, for example. And then an animation showing you this solution is also provided. Right? Of course, this is all based on years and years of research and simulation, etc. But this is the bottom line. It's bringing everything in a system. So what we are trying to achieve in my lab is that, okay, so in the middle, this is the analytics that I just talked about. All this data, how we use it to predict. But around is all the video stuff that I talked to you about, right? So you can do with videos a lot of things. You can do diagnostics of safety, you can do counting, you can do OD studies, you can do conflicts, you can do pedestrian conflicts, you can do everything, right? So now if you put them together, you have a very comprehensive system that basically can do anything. And again, the key here is AI, deep learning, so machine learning. Right? So just to conclude, and I talked to you about proactive measures, proactive safety or proactive mobility, right? Now we have the data and the ability to predict problems, to predict safety problems, to predict bottlenecks, queues, weather. We can predict everything. And therefore we can adjust so that we don't reach a very bad situation, right? This is what I mean by proactive, improving, whether we are improving safety or mobility. And then now with connected vehicles, we have this continuous connection, right? So we have, excellent data, excellent models, excellent computing capabilities. We can test everything in the simulation I talked to you about. And therefore we have, I think, a lot of opportunities. Yes, we have a lot of challenges as transportation professionals, but we have a lot of opportunities. And then I want just to finish with the Future City Initiative, because we had this discussion. So Hanyang is doing this smart city center and concept. We also, around the same time, we had the same thing, but we called the Future City Initiative. So from a research point of view, from an education, we have masters now in smart cities. And I think our masters is the first in the US in engineering smart cities. So we are thinking kind of similar. So this is my lab, UCF Smart and Safe Transportation under the University of Central Florida. So I thank you for your attention. I hope you benefited. Yeah, less than 10 minutes. So how long did I?
30 minutes.
30? Okay, so you are tired, right? So just I'll talk maybe 7 minutes. Short presentation just to give you an idea, and then let's go to the second. All right, so this is a very recent effort that I'd like to share with you, because this data, we are going to open it also for your use, everybody's use. Right? So if you're interested, let me know, by the way, and I can leave with the links for the paper that explains the data, as well as for the data where you can download them. So basically we created, and this is the link to the data, by the way, but of course you cannot type it. You can take a picture, but it's in your All right, I'm not publicizing this yet because this is very recent and we are still analyzing the data. But basically what we did is that we created AV crashes dataset. So you know that most countries, or all countries except the US, did not publish the crash data or the crash reports. So you know that this number of crashes happen, you see it on the news, but you cannot, as an analyst or a traffic engineer, you cannot put your hand on the data yet. But except California, Department of Motor Vehicles have opened their data. You can request it. And the National Highway Traffic Safety Administration, which is a federal administration, have also, you can get their data. Right? But this is going to be limited to the US. So these are basically what I'm showing you. All these dots are accidents, crashes, AV. Okay, but we split it into two parts: ADAS, Advanced Driver Assistance Systems, which is level 2, SAE level 2 automation, and it's shown in the red color, and in the blue color ADS, which is level 3 to 5. Okay. Both California and the NHTSA has both in their database. Now, when we searched more, we found that news report a lot of autonomous vehicle data in other countries. And so we started to look for news. And the news, either good description, sometimes good description and a video, because all these vehicles have a camera. So you can also get the video of the accident, right? So all the other countries that you see here, China, Europe, you have a little, one in South America, a couple in Australia. Anyway, this is all the news that we found, 52 AV crashes. So basically, we put all this and we created a database of ADS and ADAS from the 3 sources, 2 American sources and 1 news, so that we cover other countries. And these are the statistics of the number of accidents on the right side. Okay, so basically here is the NHTSA data, California DMV data, news and social media data. Again, social media to get the public sentiment. And then we use Google Maps in order to identify the location. We use Open Weather API to identify the weather. All this we combined and we created this avoid, what we call avoid database. By the way, I didn't mention at the bottom here, these are the crashes by year that we found. And this is a little bit complicated chart, but it shows you basically the percent in clear weather, the percent of location, the percent of injury. You can see also the percent of rear, right, front is where the autonomous car has been hit in this accident. Hit from the rear, hit from the side. So it gives you kind of a distribution of, and you can see differences between ADAS and ADS. Then we did the interesting part that you all hear about recently, ChatGPT, right? Okay. Is there something that we can do with ChatGPT? We use ChatGPT, right? Because basically, particularly the news part, it's a written article, right? So therefore, we can process it and ask questions to ChatGPT to identify to us based on the written, what is the reasoning for the crash, what's the attributes, what's the location, what's the type of the crash. Here, for example, is a crash from Germany. Germany do not open the data set, but we found the news from Germany. So now you can process the news article, the social media related to the news article, and then you can extract here the important information. And here we are using ChatGPT basically, or a large language model to, now one of the advantages is that ChatGPT can talk any language, right? So whether the crash is in Germany or the crash is wherever in China, no problem. It's all, we can get the information, but us as a researcher, without that, we don't know, right? We don't know all the languages. So anyway, so here, for example, you can see, this is a crash from China with the video. So now we can even analyze it. Remember, I talked to you about analyzing videos, right? So that now the video can tell us not only the traditional elements, which is weather, severity, etc., but it can tell us what is the speed, was there acceleration or deceleration, what was the maneuver before the crash, what's the angle, the surrounding vehicle. So it can actually, the video can give you even more information about the crash to help us analyze AV crashes. Right? So this is another, you can see the trajectory before the crash. We can, as I said, we can get the location also, and then identify other parameters related to the location. And also we have created this, the video processing feed into ChatGPT, and then we request from ChatGPT to write us like a proper crash report or a report about what happened, right? So it's really, we found it really useful, by the way. We wrote a paper already about that, but still under processing. It was fun, like me and my students were having fun, doing this type of work. And then here is some general descriptive statistics. So you can see here the crash time, the number of crashes, as I mentioned. The shuttles are the slow-moving ones, the one that you see them. Probably you have them in Korea. We have them on campus. Like this little bus with 10 people moving slowly. Right? So we have 6 of these crashes. And then we have 870 ADAS, 633 ABS. The years, but really the data was open starting mostly 2021. That's why more. You can see here the operation, what type of operation, and this sample, 70% was the system disengaged when the crash happened. You can see the road type. So for example, here we can see that ADAS happen more in parking lots and highways, while ADS happen more on street and intersections. So therefore, there is some differences within the two samples. Lighting condition, the speed, when the crash happened, what was the speed? Then here, I don't want to talk about it. This is like, okay, so now how complicated and do a model. So this is like a injury severity model. And we found actually a few very interesting non-traditional factors when we analyze regular crash data, things about the weather condition, about hitting a fixed object that was different than the regular knowledge that we have about crashes. So these are some, some of the models. All right, so this is the paper that we wrote. It's still under review, so it's in AR-CIV. Here is the URL if you are interested to read this paper. Actually, this paper, I think we put it also at ResearchGate. This is the #1 viewed paper in the last month or so. So people are really interested in that. If you want to read the paper, if you want to look at the data set, just when you use our data set, cite our paper. It's the only condition. All right. That's it. I just wanted to show this for fun. Thank you very much.
네, 제가 실은 너무 죄송스럽게도 발표를 2개를 부탁드렸어요. 좀 감사하게도 다 발표해 주셔서 너무 감사드리고, 제가 약간 실수를 한 게 있어가지고 잠깐 브레이크 타임을 원래 김성호 교수님 다음에 하기로 했는데 지금 브레이크 타임을 갖고 그 뒤에 프레젠테이션 3개를 이어서 하는 걸로 할게요. 그래서 지금이 3시 15분이니까 3시 30분에 다시 시작하는 걸로 하겠습니다. 잠깐 브레이크 타임 가질게요. 그럼 이제 30분이 돼서 2번째 세션으로 시작하겠습니다. 저희가 처음에 세미나 프로그램 만들 때 박기 교수님이 이제 두고 발표를 해주실 줄 몰라가지고 이렇게 만들었는데 2개를 해주셔가지고 약간 시간을 부정하게 됐고요. 그래서 저희 첫 번째 세션은 실은 키노트 스피치라고 좀 이해해 주시면 될 것 같고, 2번째 세션은 저희 이제 다양한 연구 결과들 저희 쪽에서 했던 거를 저희 학과 차원에서 같이 공유하는 거라고 이해해 주시면 될 것 같고, 그래서 제가 또 특별히 저희 교통물류공학과 학과장님께 좀 축사를 좀 부탁을 드렸어요. 그래서 박수로 모셔주시면 감사하겠습니다.
네, 이런 좋은 자리를 만들어 주신 박주영 교수님께 감사드리고요. 일단 좀 더 공식적으로 축사를 그냥 몇 가지 준비한 말씀을 드리도록 하겠습니다. 한국도로학회 도로환경 및 안전분과위원회와 한양대학교 에리카 캠퍼스 지속가능 스마트시티 융합인재 양성교육연구단에서 주관하는 국제세미나에 찾아주신 여러분 반갑습니다. 한양대학교 교통물류공학과 학과장을 맡고 있는 서원호입니다. 바쁘신 와중에서도 참석해 주신 한국철도기술연구원 손승호 박사님, 서울대학교 주양준 박사님 및 여러 전문가 분들께 감사드립니다. 한국도로학회 도로환경 및 안전분과위원회와 한양대학교 에리카 캠퍼스 지속가능 스마트시티 융합인재 양성교육연구단에서는 전통적인 도로환경, 교통안전 등의 주제와 더불어 미래교통수단과 도로와의 연계에 대한 다양한 연구 주제를 다루고 있습니다. 이번 행사에서는 미래도로 및 스마트시티를 주제로 미국의 도로교통안전 분야 저명학자인 모하마드 압두라티 교수님을 모시고 모빌리티 환경 변화에 따른 도로 환경 및 안전 연구에 대한 국제 세미나를 개최하게 되었습니다. 현재 미래도로와 스마트시티는 기존 도로에 새로운 가치를 창출하고 삶의 질을 높일 수 있는 잠재력이 매우 무궁무진하다고 생각됩니다. 이러한 미래도로와 스마트시티를 논의하는 매우 의미 있는 자리가 오늘 마련되었습니다. 여러 가지 새로운 기술을 기존 도로교통 공간에 접목하여 도시 경쟁력을 높이고 보다 이동이 편리하고 안전하고 살기 좋은 도시로 바꿀 수 있습니다. 또한 체계적인 계획 없이는 모빌리티 신기술 적용이 쉽지 않습니다. 시스템 전반에 대한 통찰력을 가지고 미래의 교통수단과 도로를 개선하는 노력들이 진행되고 있습니다. 오늘은 이렇게 여러 세계적인 전문가 교수님을 모시고 이러한 미래도로 및 스마트시티가 나아가야 할 방향에 대해서 논의해 보도록 하겠습니다. 오늘 이 자리에 함께해 주신 여러 전문가들께서 주시는 귀중한 의견을 통해 우리 도로교통 공간이 보다 발전하고 이용자가 이용하기 편리해지기를 기원합니다. 다시 한번 한국도로학회와 한양대학교 에리카 캠퍼스 지속가능 스마트시티 융합인재 양성교육연구단을 대신하여 함께해 주신 여러분들께 감사의 말씀을 드립니다. On the behalf of Korean Society of Road Engineers and Hanyang University Erika Campus Sustainable Smart City Educational Research Center, I'd like to welcome you. Please enjoy. Thank you.
네, 다시 한번 감사드립니다. 바로 이제 진행을 할게요. 김성호 교수님.
Okay, I'm Sung Kim, assistant professor at Hanyang University. So actually, Professor Park gave me two options whether I can use Korean or English. So I thought I'm gonna use the Korean, but I saw many international colleagues also. We have a special guest lecture, so I'm gonna use Korean. And if you have any questions for undergrad students, please let me know. I can use Korean later. Okay. Okay. Today I'm gonna talk about some modeling ideas. So it's a little bit different viewpoint from the previous presentation, and it is very big pressure for me right after the presentation of the world leading scholars presentation. So please enjoy. So the title is a pathway for improving transportation models for accounting for heterogeneity. So it is a little bit different field, so-called travel behavior research. So please be mindful of that. So today's presentation consists of the 4 parts. So the first, I'm gonna skim the transportation literature, and I'm gonna talk about the heterogeneity and its modeling, and I will briefly introduce an empirical example and conclude the presentation with some issues. So why heterogeneity?
heterogeneity는 참고로 한국말로 이질성이고 사람들마다 좀 다르다는 그런 인식을 하고 시작하는 겁니다.
So why do we talk about the heterogeneity? So we are living in a very complex situation, environment, and we are witnessing the era of the smart city and smart mobility. So for example, you're using micromobility or shared mobility, and we will have soon a self-driving car or urban air mobility. And also we witnessed that pandemic. So after the pandemic, people's lifestyles dramatically changed, and people got used to virtual activities like telework, e-shopping, food delivery, and so on. So in these circumstances, as a travel behavior researcher, it become more challenging. So what I mean is, it is more hard to model human behaviors, and it means it is hard to make a more accurate predictions and also make more realistic policy analysis. So how do we deal with these problems? So from my personal viewpoint is to how to account for heterogeneity of the human behaviors. And one of the strategy is the so-called market segmentation or data segmentation. It means we are assuming there is a segment of people in the population, and we are trying to segment them to understand how they are different from each other. And one of the statistical framework to model this is a finite mixture model, or the latent class model, so to speak. So today's presentation is a kind of using this approach and so on. Before that, I want to introduce transportation literature to understand what is going on. So recently I did the kind of bibliometric analysis of the transportation literature. So I collected the metadata from some two data sources. And as you can see, this is the total number of the publication in transportation literature. So up to 2020, it's more than 64,000 papers. Of course, this is very conservative numbers because I didn't count non-peer review papers or technical report and so on. So, but still, it's a big number, right? And it is dramatically increasing or exponentially growing in terms of the number of publications. It's always doubled, and so on. And because I'm interested in the travel behavior research, I try to distinguish the travel behavior papers and non-travel behavior papers by using some models. I'm gonna skip the detailed part. So this is the kind of word cloud. So which words are popping up in the transportation or travel behavior papers. So if you look at the core of the word cloud, and you can see, you cannot see the laser, right? So you can see some keywords like survey, attitude, congestion, transit, and so on. And also, there's some methodological keywords like regression, mode choice, logic, choice model, and so on. At the same time, if you look at the edge of the word cloud, there's a kind of emerging areas like model performance, algorithm, smart card, machine learning, clustering, neural network, that kind of thing. So you can see it is a kind of penetrating into the transportation literature. So as I look into the transportation literature, there's some changes over the years. So I will summarize it very in brief. So first change is the diversification of the study area. So in 1970s or old years, usually studies are the US context. So it's more than a half. But in a recent year, it is very diversified. And also remarkable change is I think the shares of the Chinese or the Asian context are kind of non-trivial right now. So that is the one change. So the second change is in the application, which means the research topic in the field. So x-axis is the year from 1990 to 2020, and y is the relative shares of the studies. So there's tons of the studies, so there's a lot of color. So you cannot see the dramatic change, but if you look at some keywords like a shared mobility or the autonomous vehicles, you can see although it is a very marginal shares, but it's increasing in the recent years. Also, there's a change of the data collection or data sources. So you can see the chart is almost governed by the red color, which means travel behavior research heavily relied on the survey data. But at the same time, if you see the green or the blue lines, so passive data may include smart card data, GPS, and so on. So you can see the shares are kind of growing in the very recent years. The last change is of the modeling. So if you see there's a tons of the methodology or models used in the transportation literature. I think one of the really some major tools are the kind of regression or econometric models or choice models. But in recent years, although it is relatively small, the machine learning or heterogeneity model has been growing. So there is a kind of change in the transportation literature or travel behavior research. So speaking of the heterogeneity, I'm gonna a little bit talk about the heterogeneity model. So it could be a little bit need background for undergrad students. So if you're interested in topic, please come to the grad school. Okay. Okay. So what is modeling heterogeneity? So typical our assumption starting point is a homogeneous behavior process or data generation process. So it means the y is the dependent variable or the behavior outcome. And we are trying to explain human behavior as a function of x, which are explanatory variable. We typically assume some single behavior function h. So here denoted by h. But as I said at the beginning, there's we think there's some segments of people. So there's types of people who have really different behaviors. So if we distinguish their behaviors like the age, H1 to a Z, then we have multiple different types of models are all together. And what we observed in the society is the consequence of the mixture of the multiple travel behaviors. And if we formulate it in an equation, it looks like this. And I want to highlight that equation maybe look like very simple, but we can customize individual elements. So it is a model structure itself is very flexible. So I'm gonna skip the details about the equation. And I want to note that there's different types of mixture model, but I'm gonna just focus on the particular type of the so-called latent class or finite mixture model. So I want to highlight that the model has been used a lot recently in the transportation literature. This is the usage in the travel behavior research. What I can say in short is the share or the number of publications using this approach is increasing. And also, when I apply the topic modeling to the literature, so there's a popping up different subdomains in the transportation. For example, travel behavioral, discrete choice modeling, community, and safety analysis, and so on. So speaking of this safety analysis, probably Dr. Abdiati or Dr. Park knows the literature. So still, safety analysis also use a lot these approaches, and you can see the number of publications is keep growing. So in a recent paper, we kind of proposed a typology of the heterogeneity that we can model. So there's several types, but for the sake of time, I'm gonna skip this part. So again, I'm very sorry for the hasty presentation. So I will just simply show an empirical example, but still it is on progress, so it is not yet. So if you are familiar with the road, there is a road named 서부간선도로, which is one of the major road in Seoul. So it is located here, and this is Seoul. So there's a 3 CBD central business districts, and the role of the 서부간선도로 is connecting the Seoul and southern western part of the Seoul metropolitan area, including here Ansan. So it looks like this. And actually there's 2 options. The first option is the ground level lanes, which are free. So it has been there for several years, but this is highly congested, always congested. So we built a new road, kind of parallel road, and it is an underground level. And also it is toll lanes, which means that there's a fare. and we need to pay for it. So it is open in September 2021. So this is the entrance of the southbound entrance. So here, the travelers will come to the near the entrance, and they have a choice whether to take the left side, which means the underground toll lane, or the right side is the free lane ground level. The fare is about $2 for entrance, and if it is a compact car, it has a half price. And usually toll lane takes a shorter travel time, like 3 to 15 minutes. And we provide a real-time information on travel time with the VNS message here. So the question is, how do we model how people choose between, make a choice between the free versus toll lane? And are people willing to pay $2 for reduce certain amount of travel time? That's the question. So we are collecting the data and still work in progress. So we are trying to undergrad students, capstone team, take a video of the entrance and tries to automatically collect, identify the vehicles, vehicle types, and the traffic counts. So it is still on progress, so it is not yet finished. So but the problem is we have preliminary data right now. So when we apply the typical choice model to the data, what we observe is that there's a very small negative travel time coefficient. What it means is people are not really sensitive to the travel time difference. So they don't make a change on depending on the travel time. So I also applied a little bit more advanced model to accounting for different types of heterogeneity. But what I found is that there's a positive coefficient. So what it means is people tend to choose longer travel time lanes, so which is a very counterintuitive. So what is happening here? So in this situation, we assume our approach was we assume all the road users or travelers are really choice makers. So they will make a choice between the toll versus a free lane, depending on the travel time difference. But actually, it is not the case. So for some segment of people, really do not make a choice and always choosing the toll lanes or always choosing the free lanes. So I'm the one of the person here actually. And also there's a lot of people always choosing the free lanes because I didn't say in the before, but if you are taking the free ground level lane, there is a middle exit. So some people are exiting middle of the stretch because they're going different destinations. So in that case, the toll lane is not an option for them. So if we are really taking them as making a choice, then our inference is really wrong. So this is where here comes the latent class. So what I propose is here. So we need to identify who are the actual choice makers or who are the not choice makers. But what I want to say is, if we are simply applying the typical latent class model or the other machine learning models, I can guarantee you that the results will not intuitive because it includes that kind of people. So that's why we need to embed our knowledge into the latent class formulation. So that's where really analysts should put our knowledge into the model formulation. So that's one of the drawback, one of the key points. So when we simply apply this model, I saw the right-hand side that the conventional model will give the very counterintuitive results, whereas the proposed left-hand side model will give the quite meaningful results. So I didn't bring the results for the sake of time. Okay, so I will move on to the next section, but how many minutes do I have?
10 minutes.
Okay. So I think I kind of missed because usually audiences are undergrad students, so I think the topic is a little bit grad level things. So please forgive me. So, but the problem is there's several issues here. So one thing is the typical our approach is we are assuming that kind of a heterogeneity is not observable. So what it means is we cannot see that heterogeneity, but so that's why we apply the model and identify based on the data or the model. So if, as I said, if possible, observed heterogeneity is preferred over unobserved heterogeneity because if we apply really heterogeneity model, sometimes we're really facing at the end, the results are very interesting and meaningful, but at the end, it is hard to make a policy recommendation. So the box is one of the anonymous reviewer of the paper and kind of casting a doubt about the usefulness or the validity of the results. So I want to highlight this situation, particularly for some grad students who are just looking for fancy models. I'm gonna skip this part. And also another issue is a kind of, so to speak, error correlations. So what it means is, what if the mechanism, how people belong to the segments and how people generate behaviors are kind of associated. So in that case, the problem is so-called self-selection problems in the literature. So if we really do not control that issue, self-selection effects, then our inference will be wrong. So that is a very classical example. And one of the colleagues, the economic professor, got a Nobel Prize with this idea in 1970. No, sorry, 2000. So recently we published a paper why we need to control that self-selection effects with some empirical results. And also we applied that idea to the advanced latent class model to embed the error correlation structure into the model. And I'm gonna skip this part. Okay, so it was a very hasty presentation, but I want to conclude that transportation literature has been growing a lot. And especially, you saw that recent increase are due to the application of the smart city and smart mobility. And in these circumstances, I believe the modeling heterogeneity will be more important than before. So I think any idea of the heterogeneity or that kind of model will be very important in the future applications. So I'm gonna skip this part. And I just want to express my gratitude to my PhD advisor, Dr. Peterson Octarian at Georgia Tech, and also undergrad capstone team, Northern Link, for their data collection and preliminary analysis of the data. Okay, this is the list of what I referred. And thanks for you listening. And if you have any questions, I really want to get your opinions or having a discussion about the idea. And I want to collaborate with you and also if you're a student, I'm open for hiring probably. Yeah, 감사합니다.
네, 감사합니다. 다음 발표로 넘어갈게요. 다음 발표는 서울대학교의 주양준 박사님이 발표를 해주시겠습니다.
네. 안녕하세요. 저 서울대학교 지금 도로환경 종합연구소에서 박사후 과정으로 있는 양준입니다. 앞에 두 분께서 영어로 발표를 해주셨는데 저는 일단 한국말로 일단 발표를 하는 거에 양해를 부탁드리겠습니다. 일단 앞에 두 분께서 너무 저명한 학자시고 그분들 뒤에 바로 하는 거에 대해서 저도 굉장히 많은 부담을 느끼고 있지만 한번 최선을 다해서 지금 제가 발표드릴 주제에 대해 발표드리도록 하겠습니다. 일단은 굉장히 좀 생소한 언어가 지금 들어가 있어요. 인공장애론이라는 용어를 썼는데 뒤에서 말씀드리겠지만 이 교통상충이라고 하는 거는 아티 교수님께서 말씀 주셨지만 사고가 발생하기 이전에 그러니까 관측되지 않은 그런 상충들을 평가하는 기법에 관한 겁니다. 이런 상충을 평가할 때 방법들이 여러 가지가 있는데 차량들이 어떤 우리가 전기장에서 발생시키는 전기장이나 그런 자기장 이런 개념을 이제 사람이 발생시킨다라고 보는 관점에서 이 인공장애론이라는 용어가 나오게 되었습니다. 그래서 일단 교통상충이라는 거는 어떤 주행 상황이 있으면 이 상황을 어떤 센서로 받아가지고 어떤 과정을 거쳐서 이 상황이 지금 위험한지 아닌지를 판별하는 어떤 과정의 하나라고 보시면 될 것 같고 이 방법은 사고가 일어나기 전에 우리가 사고 위험이 높은지 또는 사고에 관한 어떤 조치를 취한 뒤에 이 조치가 잘 적용이 됐는지 평가할 때 굉장히 중요한 요소로 작용하게 됩니다. 이전에 나왔던 내용이긴 한데 사실 저희가 관측할 수 있는 사고는 이 검정색 부분에 한정되어 있어요. 그래서 실제로 위험하지만 관측되지 않았던 밑에 저런 컴플리트 상충들을 평가하는 것이 이 연구 또는 교통 상충을 평가하는 연구들의 핵심이라고 보시면 될 것 같습니다. 당연하게도 위험한 사고들은 관측하기가 어렵고 그거에 따라서 어떤 정책 효과들을 평가하거나 정책에 어떤 개입이 필요한지를 알 수가 없어요. 그렇지만 이런 상충들은 우리가 운전하는 상황에서 자주 발생하기 때문에 교통공학적으로 모델링을 하거나 아니면 우리가 어떤 개입이 필요한지를 판별하기에 아주 적합한 그런 방법이라고 보시면 될 것 같습니다. 그래서 교통상충이라는 거의 가장 기본적인 거는 우리가 교통상충을 평가할 때 어떤 특정 값으로 치환을 해야 된다는 것입니다. 예를 들면 어떤 주어진 상황이 있으면 이게 안전하다, 아니다 이렇게 주관적인 평가가 아니고 어떤 숫자로 하나로 나와야 된다는 게 첫 번째 교통상충 평가가 가져야 될 조건이라고 보시면 될 것 같습니다. 두 번째는 어떤 교통 상황이든 간에 위험한 상황이 더 안 위험한 상황보다 그 위험도가 더 높게 평가되면 안 된다는 겁니다. 예를 들면 어떤 상황에서는 더 위험하고 어떤 상황에서는 안 위험하고 이런 상황들이 뒤죽박죽 섞여 있으면 우리가 이 지표라는 것을 신뢰할 수 있을까라는 측면이죠. 따라서 위험한 상황에 대한 어떤 정의가 되어 있고 그것들이 어떤 하나의 지표로 쭉 일렬로 이제 줄 세우기를 하는 거라고 보시면 될 것 같습니다. 그래서 이 교통상충 평가가 가지고 있는 현재 이슈들을 지금 정리를 해봤어요. 그래서 지금 이 교통상충 평가가 어려운 이유는 지금 원으로 표시된 지금 4가지로 정비가 되어 있는데요. 일단 가장 중요한 거는 운전자마다 운전 성향이 달라요. 그래서 운전자가 이제 지금 차선 변경을 할 건지 아니면은 양보를 해줄 건지 이런 것들에 대해서 우리가 각각 구분을 해야 되는데 운전자별로 이게 너무 다 다르다 보니까 우리가 어떤 모델링 하는데 좀 어려움이 있는 거죠. 또 우리가 차선 변경할 때 상충을 평가할 수 있는 모델을 만들었어요. 근데 이 차선 변경에만 평가할 수 있는 모델이 차선 변경이 아닌 앞차를 따라가는 거라던가 아니면 양보하는 상황이라던가 이런 거에는 적절하게 대응되지 못하는 점. 그래서 각각 상황별로 우리가 어떤 평가를 기법을 써야 되는지를 이제 다 상황별로 설정해야 되는데 이제 운전을 해보시면 알겠지만 우리가 모든 상황들을 다 구분을 해 놓을 수는 없는 거잖아요. 그런 부분에 있어서 어떤 상황이 유리한 상황인지 다 시나리오별로 평가를 해야 된다는 지금 한계가 있고요. 또 마찬가지로 이게 커브길인지 경사로인지 이런 것들 그리고 우리가 모르는 요소들도 있고 이런 부분들 때문에 교통상충 평가가 지금 좀 어려운 부분이 있다고 지금 말씀드릴 수 있을 것 같습니다. 그래서 그럼 교통상충 평가가 어때야 되는가에 대해서 말씀을 드리자면 지금
이 상황이 차선 변경인지 아니면 앞차를 따라가는 상황인지 우리가 매 시간 구분을 해야 된다면 그 경계가 매우 모호해질 수 있어요. 그래서 이런 상황에 따른 구분이 전혀 필요 없는 모델이 일단 좋은 모델이다라고 말씀드릴 수 있을 것 같고, 두 번째는 밑에 그림을 보시면 지금 빨간색 것만 보면은 우리가 안전하다라고 말할 수 있고, 파란색 것만 보면은 안전하다, 이렇게 두 개의 안전한 상황이 모였는데 우리가 이 상황 자체를 보면은 되게 위험해 보이죠. 그래서 이런 위험한 상황이 왜 위험하냐? 한 대 차량뿐만 아니고 내가 여러 대 차량과 동시 상호작용하는 경우에 대해서는 우리가 조금 더 위험한 상황이라고 판별을 해야 된다라는 거죠. 그래서 여기뿐만 아니라 또 한 가지 상황이 있는데, 저 1번이랑 3번이랑 정해진 아까 그 상황에서 만약에 3번이랑 차량이 굉장히 운전자가 공격적이어서 이 차가 어떻게 움직일지 모른다고 가정해 봅시다. 그러면은 이 차가 움직이는 평균적인 어떤 행동을 가지고 보면은 지금 이 상황은 안전할 수 있어요. 근데 이 사람이 굉장히 공격적이어서 어떻게 운전할지 모른다, 이런 상황에 대해서는 안전성 평가가 지금은 위험하다라고 평가를 해줘야 되는 상황이라는 겁니다. 마지막으로는 이거는 좀 학술적이랑은 좀 다른 얘기긴 한데, 어쨌든 우리가 교통 상충 평가라는 거는 어떤 하나의 지표로 어떤 주행 상황들을 일렬로 나열하게 되잖아요. 그럼 그 상황에 나온 결과가 숫자예요. 그러면 예를 들면은 지금 위험한 상황이 10입니다. 11입니다. 10입니다. 이런 식으로 말해주는 것보다 어디가 위험한지, 그리고 그러면 내가 그 위험을 통해서 내가 어떻게 주행 상황을 바꿔야 되는지, 이런 것들을 나타내줘야 되려면 어디가 위험한지를 시각화해줘야 된다는 거죠. 그래서 결국 정리를 해보면 주행 상충 평가라는 건 알아봤습니다. 지금 아까 말씀드렸듯이 주행 상황이라는 어떤 하나의 관측치를 가지고, 뭐 하나의 관측치를 볼 때 지금 현재 상황만 볼 수도 있고 이전에 관측된 여러 대의 상황을 볼 수도 있죠. 그래서 여러 개의 주행 상황의 어떤 기록을 가지고 지금 상황이 위험한지 안 위험한지 요거를 어떤 하나의 함수를 만드는 과정이라고 보시면 될 것 같습니다. 그래서 본 연구에서도 요거를 할 건데, 아까 말씀드린 세 가지 요소, 다양한 상황에서도 동시에 적용될 수 있어야 되고, 그리고 여러 대의 위험이, 그러니까 여러 대가 동시에 상호작용하면 조금 더 위험한 상황이라고 평가를 하고, 또 불확실성이 많으면 더 위험하다라고 동시에 판별할 수 있는 이 세 가지 조건을 모두 만족하고, 여기에 더해서 시각화를 적절히 해줄 수 있는 기법을 제안을 하는 것을 이제 목표로 삼았습니다. 그래서 기본적인 컨셉을 먼저 소개해 드리려고 합니다. 일단은 우리가 가장 이 위험을 느낀다 또는 위험한 상황이다라는 거에 대한 어떤 정의에서부터 시작을 해야 됩니다. 그래서 가장 위험한 상황이란 뭘까라고 생각하면은 차량들이 움직이고 있겠죠. 얘네들이 움직이는 궤적들이 만약에 내가 겹치는 순간은 결국 그건 사고잖아요. 그래서 이 차량들이 움직이는 궤적들을 어떤 확률 분포로 나타낼 수 있겠죠. 이 점에 위치할 확률이 얼마 이런 식으로 지금 4개의 확률 분포로 나타내져 있는데, 이 4개의 확률 분포들이 겹치는 거는 결국 우리가 상충이 일어날 것이다. 즉 내가 앞으로 위치할 공간과 다른 차량이 위치할 공간이 겹쳐 있다는 거잖아요. 그러면 그건 바로 우리가 상충이다라고 정의를 할 수 있겠고, 이 각각의 디스트리뷰션, 이 각각 어떤 인공적인 장, 위험장이다라고 해서 리스크 필드라고 이름이 붙여져 있습니다. 그래서 이 리스크 필드들이 이루는 이런 어떤 디스트리뷰션이 겹치는 부분이 있겠죠. 이 겹치는 부분이 바로 상충이고, 이 상충의 크기가 크면은 상충이 발생했다라고 말할 수 있는 겁니다. 저 조금만 자세히 넘어가는데 간단하게 하고 넘어갈게요. 요 개념은 이제 우리가 앞에 궤적을 예측을 하는데, 너무 뒤에 있는 궤적은 별로 위험하지가 않아요. 우리가 10초 뒤 차량이 움직이는 거를 다 고려하진 않잖아요. 그래서 적절하게 할인을 해주는 겁니다. 그래서 절반씩 할인을 해주고, 할인된 걸 가지고 이제 우리가 상충을 평가하게 되는 거예요. 그러니까 많이 뒤에 있는 거는 우리가 전혀 위험하지 않다라고 보게 되는 거죠. 그리고 실제로 우리가 어떤 점을 가지고 계속 얘기를 할 수 있지만 사실 차는 점이 아니잖아요. 그래서 차 안에 우리가 어떤 예측을 할 때 기준점이 필요하겠죠. 이 프레딕션 포인트가 이 차 주변을 이렇게 둘러싸고 있다고 보면 될 것 같습니다. 그래서 실제로 우리가 바운딩 박스라고 하는 걸 가지고 안전성 평가를 하는데, 실제 운전하다 보면은 조금 폭을 두잖아요. 그 개념이 이제 세이프티 마진으로 들어가고 앞차랑 뭐 경사로에 있으면 또 바로 붙이면 안 되니까 그런 스탠스틸 디스턴스까지 넣어서 이 프레딕션 포인트가 이 어떤 인공적인 점유 공간을 우리가 점유하고 있다라고 보시면 될 것 같고 이건 이제 모델링을 어떻게 할지에 대해서 간략하게 넣고 쉽게 말해서 그냥 저 박스 안에 저 점들이 그냥 가득 차 있다라고 가정하면 하는 모델입니다. 그리고 마지막으로 차가 또 빨리 움직이면은 사고의 심각도가 높잖아요. 그러니까 그러니까 차가 빠르면 사고가 날 가능성도 높고 심각도도 높으니 그거만큼 리스크 필드 더 위험을 많이 느낀다라고 가정한 이제 모델이라고 보시면 될 것 같고요. 결과적으로 보면은 식은 이런 식으로 나옵니다. 그래서 어떤 차가 이거를 이제 옆단에서 보면은 각 차들의 이제 점유하는 위치 공간에 대한 어떤 디스트리뷰션들이 다 합해져서 이제 검정색의 어떤 분포가 나오고 이 검정색 분포끼리 이제 여러 개가 생기는 거죠. 내 차 주변에 모든 이 검정색 분포들을 가지고 우리가 상충을 평가를 하게 됩니다. 그럼 결국 이런 식으로 나오는데 그럼 빨간색으로 나오는 저런 이제 상충 장애라고 정의를 했었죠. 요 상충 장애 크기가 바로 우리가 어떤 새로운 컴플리트 상충이라고 볼 수 있는 겁니다. 그래서 보면은 이게 기존에 사용했던 지표들이에요. 기존 지표들 보면 타임 투 컬리전이나 뭐 포스트 인크로치먼트 타임 이런 걸 보면은 지금 현재 주행 상황만 보고 이전에 이 차량들이 어떻게 움직였는지 이 사람들이 어떤 특성을 가지고 있는지 전혀 알 수가 없습니다. 그래서 이런 점들도 좀 보완을 하고 또 가장 큰 문제가 아까 얘기가 잠깐 나왔긴 했지만 이 차량들은 점이 아니에요. 점이 아닌데 이대로 쭉 달리고 있다 보면은 이 점들끼리 겹치지 않으면은 전혀 사고의 위험이 없다라고 하면은 조금 우리가 그렇게 동의하지 못하죠. 하지만 이게 점이 아니고 이 차량들이 점유하는 면적을 가지고 보면은 얘네들 간에 어떤 겹침이 존재한다. 그래서 이 겹침의 정도가 크면 우리가 위험하다라고 말할 수 있는 거죠. 그런 부분에 있어서 기존의 방법론과 조금 차별점이 있다라고 말씀드릴 수 있을 것 같습니다. 그래서 그러면은 결국 예측을 해야 되잖아요. 그래서 고속도로 상황에서 가장 이제 사고가 날 만한 6개의 차량을 매칭을 하고 그 차량을 이제 1초 동안 관측을 한 걸 가지고 앞으로 6초간 이 내 주변의 차량들이 어떻게 움직이는지를 예측을 하는 이제 문제를 풀게 됩니다. 사실 이제 딥러닝 구조를 쓰긴 했는데 어쨌든 굉장히 복잡한 예측 문제를 하잖아요. 내 1초에 6대 차량의 어떤 궤적을 가지고 6초 뒤까지 예측을 하는 거다 보니까 일반적인 통계 모델로는 어려워서 딥러닝 모델 구조를 활용을 했고요. 그리고 궤적 예측에 있어서 가장 중요한 이슈 중에 하나는 일단은 우리가 사실 평균을 예측할 수 있잖아요. 궤적의 어떤 평균을 예측할 수 있는데 실제로 궤적 예측을 해보면은 지금 어떤 차량이 예를 들면 트래젝토리 캔디데이트 1, 2, 3가 있다고 봅시다. 이 1, 2, 3가 각각 동일한 확률을 가지고 있다고 우리가 가정을 해보면은 얘네들이 실제로는 1번으로 3분의 1, 2번으로 3분의 1, 3번 궤적으로 3분의 1 이렇게 갈 수 있는데 이걸 평균을 내버리면 우리가 초록색으로 나오는 아무랑도 관련이 없는 어떤 궤적이 나오게 되는 거죠. 그래서 이런 문제를 피하기 위해서는 이 각각 분포들이 확률적으로 이루어졌다라는 가정이 필요합니다. 이게 가장 기본적인 가정이고 그러면 우리 문제에서 어떻게 해야 되느냐 어떤 차량이 있을 때 감속이냐 가속이냐 두 개 중에 하나 좌회전, 우회전, 직진 이렇게 해서 총 6개의 가능성이 있다라고 가정을 합니다. 그래서 이 6개의 가능성을 가지고 우리가 얘네들의 가중합해서 어떤 차량의 확률을 모사할 수 있다라고 이제 가정을 하면 됩니다. 그래서 실제로 보면은 이건 내 주변 차량들의 궤적을 예측을 한 건데요. 왼쪽 같은 경우면 굉장히 불확실한 상황에서 이 차들이 좌우로도 어디로 갈지 모르고 내 진행 방향으로도 어디로 갈지 몰라서 굉장히 디스트리뷰션이 분산되어 있는 걸 볼 수 있어요. 반면에 오른쪽 같은 경우는 굉장히 이 차들이 어떻게 움직이는지 이 프레딕션 모델이 확신을 하고 있는 걸 볼 수 있습니다. 그래서 분명히 왼쪽 같은 상황이 조금 더 우리는 불안한 상황이죠. 어떻게 움직일지 모르니까. 이 상황에서 좀 더 보수적인 평가를 할 수 있게 만든 거라고 보시면 될 것 같고요. 마지막으로 스킵하자 마이너한 이슈이긴 한데 우리가 이중 접근을 해야 돼요. 근데 이게 실시간으로 하다 보니까 꽤 모델이 무거워져서 한번 근사를 시킨 거라고 보시면 될 것 같습니다. 요건 넘어가겠습니다. 그래서 근사를 하게 되면 결국 우리가 실제 값을 얻는 데는 한 10초, 20초 걸릴 수 있어요. 근데 우리가 그렇게까지 정확할 필요는 없잖아요. 그러니까 어느 정도 정확하면은 우리가 실시간성을 쓸 수 있잖아요. 그래서 우리가 보통 이게 0.1초 단위로 모든 계산이 끝나야 되는데, 그래서 0.1초 정도 걸리려면 어느 정도 되는지, 그러니까 평균적인 에러가 어느 정도 되느냐를 본 표라고 보시면 될 것 같고요. 그래서 보시면은 지금 검정색으로 표시된 게 내 차가 아니고 내 뒤에 차예요. 내 뒤에 차가 실제로 저런 어떤 인공적인 장을 생성하고 이 생성된 장이 파란색으로 표시된 내 차. 내 차와 어떤 겹치는 빨간색 순간, 지금 그림 C에 나와 있는데 이 겹치는 공간이 바로 위험한 공간이죠. 이게 어느 순간 넘어가면 우리는 차선 변경을 못하는 거예요. 하면 안 되는 거죠. 그러니까 그런 식으로 우리가 상충을 평가할 수 있게 되고, 이렇게 되면은 점으로 가정했을 때보다 훨씬 더 보수적인 평가 결과를 얻고, 그러니까 우리가 좀 더 이 차를 믿을 수가 있겠죠. 그래서 가까이 보면 이런 식으로 나오겠고, 이 차량 바닥면에 어떤 박스들이 뿌려져 있는 형태로 지금 나와 있어요. 이 박스의 높이가 높으면 그만큼 위험한 공간이라는 거고, 빨간색이 높으면 그만큼 다른 차량 상충할 가능성도 높아진다라고 보시면 될 것 같습니다. 그래서 이거를 애니메이션 안 되네요. 일단은 이거를 이제 매 순간순간마다 이렇게 우리가 그릴 수 있겠죠. 0.1초마다 구할 수 있으니까 0.1초마다 플러스를 해보면 이런 식으로 빨간색 영역들이 발생하고, 이것들이 많아지면 차가 갑자기 뒤로 가죠. 이런 식으로 상충이 얼마나 발생했는지를 매 순간순간 연속적으로 평가할 수 있다. 이렇게 말씀드릴 수 있을 것 같습니다. 그래서 실제 데이터에다가 적용해 본 거고요. 미국의 한 도로에 대해서 적용을 해본 결과, 미국의 한 도로에서는 차선 변경이 한 4.2% 그리고 대부분의 이제 앞차를 따라간 상황이긴 했는데, 이 둘 사이의 전환이 우리가 굳이 구분을 안 해도 하나의 지표로 평가할 수 있으면 우리의 본래 목적을 만족하게 되는 거죠. 그래서 궤적을 한번 그려보면은 이건 시공도예요. 그 수업 시간에 아마 배우셨을 테지만 그냥 차량의 속도랑 어떤 이 차들의 시간 그리고 위치 그래프를 나타낸 건데, 지금 보면 어떤 상충들이 굉장히 많이 나타나고 있죠. 앞차가 뒤로 가면서 갑자기 느려지면 내 차량이 갑자기 가까워지잖아요. 그런 것들을 나타낸 거라고 보면 되고, 그래서 지금 밑에 크래시 리스크를 보면은 어떤 특정한 길을 따라서 이렇게 쭉쭉 펴져 나가는 거 보니까 이거는 이 데이터가 이 상충을 연구하기에 굉장히 괜찮은 데이터다라고 볼 수 있을 것 같습니다. 그래서 실제로 보면은 지금 요거는 A, B, C, D라고 나와 있는 요거는 지금 차선 변경하고 바로 앞차를 따라가는 추정 상황을 연속적으로 나타낸 그래프입니다. 그래서 B에서 보면은 그림이 잘 보일지 모르겠는데 지금 차선 변경을 하고 있는데 지금 L0랑 F0라고 나와 있는 이 구간의 갭이 굉장히 짧아요. 그렇다 보니까 이거는 굉장히 위험한 상황이죠. 그래서 사실은 차선 변경을 하면 안 되는데 일단 이 차는 차선 변경을 하고 있습니다. 그래서 순간순간 이 차선 변경이 완료됨에 따라서 얼마나 이 지표가 더 위험하다라고 나타내는지를 보여주고 있는데요. 지금 보면은 검정색으로 나타낸 게 이 빨간색으로 나타낸 영역의 부피를 모두 다 계산한 값입니다. 그래서 빨간색 부분의 이제 크기를 보면은 처음에 B에 있을 때는 굉장히 작다가 C로 가면은 L0로 나타낸 이 차량과 상충이 엄청 커져서 엄청 지금 굉장히 끝에 값까지 올라가고 있죠. 이런 식으로 매 순간순간 연속적으로 나타날 수 있습니다. 이 방식이 왜 좋냐라고 하면은 결국에 아까 말씀드렸던 이 차량이 점이라고 가정하지 않았잖아요. 이 점이 아니고 어떤 공간을 점유하기 때문에 매 순간순간 신뢰도 있는 값을 얻을 수 있습니다. 왜 그러냐면 이 파란색으로 나타낸 지금 파란색 0.0초부터 지금 1.7초까지 나타내는 지점이 이전 차량들과 어떤 겹치는 구간, 겹치는 점이 존재할 때예요. 그리고 빨간색이 내가 이제 출발할 때, 네, 출발 차선에서 벗어나고 두 번째 내가 도착 차선에서 있을 때 이제 그쪽 차량들과 상충하는 점이 존재할 때예요. 그렇다 보니까 상충점이 존재하지 않으면 갑자기 사라지고 존재하면 갑자기 생기고, 그러니까 위험함과 안 위험함이 너무 왔다 갔다가 빠른 거죠. 그러니까 위험하다가 0.3초 뒤에 안 위험해. 이런 식으로 이제 분석 결과가 나오다 보니까 우리가 이 지표를 신뢰할 수 있을까라는 측면에서 조금 제한한 지표가 조금 더 신뢰도를 많이 얻었다. 여기에 더해서 앞차가 기존 지표들은 앞차가 좀 더 느리게 와야 조금 더 위험하다고 판단하거든요. 근데 제한한 지표는 앞차가 느리지 않고 충분히 가까웠고 이 차량들이 겹치는 위치가 많으면 많을수록 더 위험하다고 판단하기 때문에 훨씬 더 믿을 만한 지표다라고 말씀드릴 수 있을 것 같습니다. 그래서 기존 지표들과 어쨌든 통계적인 연관성을 한번 확인해 봤고요. 그래서 타임 투 컬리전이랑 크게 관련이 없었는데 가장 큰 이유는 타임 투 컬리전은 앞차가 더 빠르면은 위험도가 제로다라고 말을 해버리는데 그걸 실제랑 제가 생각할 때는 맞지 않다고 봤어요. 그래서 그런 부분에 있어서 상관성이 굉장히 적게 나왔고 포스트 인크루치먼트 타임, 그러니까 이 앞차가 떠나고 난 이 지점을 내가 몇 초 뒤에 가느냐랑은 굉장히 유사한 결과가 나왔다라고 보실 수 있을 것 같습니다. 그래서 제안된 지표는 이 PET라는 지표랑 조금 더 가까운 지표고 나머지 두 개의 지표도 비슷한데 결국에 이 앞차가 이 차랑 가까워져야 정의가 되는 지표들이에요. 그러니까 앞차가 조금이라도 빠르면은 정의가 안 되는 지표들이다 보니까 통계적인 상관성이 그렇게 많이 나오진 않았다라고 말씀드릴 수 있을 것 같습니다. 그래서 이 지표들을 보면은 아까 그 미국 데이터에다가 적용을 해봤다고 했잖아요. 그래서 한 15분 동안 나타낸 이 제한한 지표인 Sum of Conflict Field 요 지표들 한번 CDF를 그려봤는데 그러면 결국에 이 CDF가 상위권에 있는 요 운전자들은 빨간색으로 표시된 운전자들은 위험하게 운전을 하는 거고 파란색으로 된 운전자들은 중간, 초록색은 이제 좀 안전하게 운전하는 사람들 이런 식으로 우리가 운전자가 어떻게 운전하는지도 알 수가 있고 이들 보면은 어떤 상황에서 위험하게 운전하는지 그런 것들도 이제 추가로 분석하고 추후에는 이런 SCF 지표들을 이용해서 사고가 얼마나 날 가능성이 얼마나 되고 이런 것들까지 이제 활용할 수 있을 것 같습니다. 그래서 마지막 보면은 이제 이 리스크 필드라는 지표가 어쨌든 미래 가중치를 이제 할인을 하잖아요. 이 할인하는 어떤 파라미터에 따라서 어떻게 이 그림이 이 리스크 필드가 나타나는 이 분포가 어떻게 달라지는지를 나타내는 어떤 그림이라고 보시면 될 것 같습니다. 그래서 보면은 반감기가 짧으면 당연히 앞에 것만 보니까 굉장히 리스크 필드가 앞에만 보는 거죠. 그러니까 내 앞에 어느 정도 아무런 차량이 없으면 안전하다고 보는 어떤 지표가 되는 거고 이게 좀 더 반감기가 길면은 좀 더 멀리까지 보는 거죠. 원시간적으로 내가 앞에 몇 초 뒤에까지는 용인을 하겠다. 그러니까 그게 넓어지는 거죠. 좀 더 보수적인 운전자가 될 것 같습니다. 그래서 보면은 결국 우리가 어떤 교통 상충이라는 걸 평가함에 있어서 기존 지표들이 가지고 있던 한계들이 극복하기 위해서 인공장애라는 개념을 도입을 했어요. 이 인공장애라는 개념을 통해서 좀 더 실제랑 우리가 납득할 수 있을 만한 어떤 상충의 지표들을 우리가 일렬로 나열을 할 수가 있었고 그리고 그 과정에 있어서 운전자들이 가지고 있는 불확실성을 딥러닝 모델을 통해서 확률적으로 모사를 했죠. 그리고 이거를 실제로 어떤 실제 데이터에 적용을 해봤습니다. 그래서 보면은 결국에 우리가 차선 변경인지 아니면 추종 상황인지 구분할 필요가 없고 그리고 여러 차량이 더 동시에 상충을 하면은 이 상충의 크기가 커지겠죠. 그래서 여러 대의 상충에 대해서도 동시에 평가를 할 수 있고 확률적인 모형을 사용했기 때문에 불확실성에 대응할 수 있는 어떤 모델을 제안을 한 거라고 보면 될 것 같고요. 그에 따라서 우리가 어떤 지점에서 좀 위험한지 이런 것까지 비주얼라이제이션 할 수 있고 실시간으로 아까 근사를 했었죠. 그래서 0.1초마다 이제 계산할 수 있게 모델을 가볍게 했다라고 보시면 될 것 같습니다. 그래서 향후 연구로는 지금 고속도로 데이터만 했었잖아요. 그래서 이걸 드론 데이터나 아니면 보행자가 섞여 있는 그런 데이터셋에도 적용하면은 충분히 이제 확장 가능성이 있는 그런 방법론이다라고 보실 수 있을 것 같고요. 네, 그래서 뭐 신호등이 없거나 좀 보행자랑 이제 차량이랑 뭐 자전거랑 섞여 있는 이런 상황이나 이제 대학 캠퍼스나 이런 데에서도 충분히 적용 가능하고 시각도 가능하기 때문에 너 위험하다 이런 식으로 경고를 주는 것도 가능하겠죠. 네, 이상입니다. 감사합니다.
박사님 감사합니다. 저희 이제 마지막 발표입니다. 실은 저희 연구실에 석합하고 있는 이상재 연구원이 여러분들께 발표를 드리겠습니다.
Hello. Okay. Hello, my name is Sang Lee from Hanyang University, and I'm gonna present my research by English. Because this seminar attends many international guests, so I will gonna try my best. But my English skill is so bad, so some of you will not understand very well. If someone thank you. If someone wants to know the detail of the study, please let me know. And again, I'm now studying at Professor Park's lab. And my research topic is driving safety evaluation of this car following situation by autonomous and manual vehicles at urban interactive road facilities. In Korean, in shortly, 도심부에서 자율차와 혼재되어 주행하는 상황에 주행안전성 평가입니다. First, autonomous driving without driver intervention will be commercialized with the development of technology. And in the future, autonomous vehicle, which we call as AV, and manually driven vehicles, which we call as MV, will be driving on the same road. AV has a shorter cognitive response than MV, and so a shorter interval is required to avoid crashes. Therefore, when AVs are driving, the risk and the probability of crashes can be reduced. Since the driving behavior of AV and MV is different, driving safety will be affected by the interaction of AV and MV. This study aims to evaluate the driving safety for car-following scenarios involving AV and MV and on urban roads, and to identify the driving safety vulnerability section for each road. And this slide shows the overall framework of this study. We conduct the research by these 3 steps, like test scenario setup, and data collection and processing, and selection of vulnerable section. First, we set the function and behavior of AV and draw the network of urban interactive road. And then we conduct the driving simulation and produce the driving safety indicators of longitudinal and lateral and inter-vehicle. Finally, we analyze the data by descriptive statistics and speed profiles of driving safety indicators, and then comparison of driving safety indicator, and finally, derivation of the driving safety vulnerable section by analysis of errors, which we call as ANOVA. To implement the AV in the simulation, this study performed 3 steps. First, we defined the requirements to implement the ideal autonomous vehicles. And second, behaviors of AV were investigated, and some were selected, which necessary for the simulation. And third, so AV behavior was referred to the autonomous driving system of the National Highway Traffic Safety Administration. We call it NHTSA, and third, we produced the AV driving algorithm in the consideration of the requirements of the AV, and was put into the simulation. So the detailed description of each step will be explained in the next following chapter. So step 1, this study set the requirements of AV maneuvering by this assumption. And the assumption is driving behavior of AV and MV is different. First, AV cannot cause the collision by themselves. Because AV maneuvers with safety and no crash caused by the driver's mistake due to the fast reaction time. And second, AV driving smoothness. And AV tries to drive consistently without significant change in speed and no sudden change in longitudinal and lateral behavior except a special event. And last, AV driving deterministic. Unlike human driver, AV keep constant driving behavior under the same conditions. This study set these three requirements and driving tests on AV satisfy this. And step 2 is the AV behavior abstraction. Because we cannot implement the exact driving algorithm of other AV company, this study abstract the autonomous driving system of the Nissan. Abstraction is simplifying the core concept in real. Abstraction is the simplifying the core concepts in real functions and systems. And among the various systems proposed by Nissan, behavior was selected that mainly used in urban roads. The selected behavior is maintaining speed and car following and navigate intersection and crosswalk and navigate roundabout and U-turn. The behavior of AV was produced as an algorithm and implemented in the simulator through the script editor module in the scanner. Scanner is the driving simulation software that can implement the virtual space and control the vehicle according to the sequence. And step 3 is the implementation of AV driving algorithm. This is the example of the navigate crosswalk algorithm, and the algorithm are converted to the programming language of the scanner scenario. First, autonomous vehicle indicate the crosswalk, and then stop at the stop line with the calculating remain distance and speed distance and speed near to stop. And AV check the pedestrian crossing, and if no one is crossing, AV pass the crosswalk. Next is driving simulation. This study implements the car-following situation between vehicles using multi-agent driving simulator, which called as MADS, and which could link the two driving simulators in real time on the same road. So MADS can analyze driving behavior based on the interaction between vehicles. And this is the main theme of simulator synchronization. Through the network connection of driving simulation, information of the vehicle can be shared on simulation. And this could analyze driving behavior of AV in mixed traffic. This page shows the simulation of simulation scenario. Total 30 subjects were recruited, and date is December 23 to February 5. This image shows the simulation scenario of AV. And as you can see, this driver on the left side did not control the maneuvering of the vehicle because she drives in the AV, and this driver on right side controls the vehicle to follow the leading vehicle. Next is the network of urban interrupted road by referring to the road structure, design, guidelines, and the AV behavior. This network tries to implement the road structure and signals in urban roads and driving tasks of and driving task of each section is such as linear of the flat line and U-turn and signal intersection and non-signal intersection and longitudinal slope plus 5% uphill and downhill and roundabout and crosswalk. The subject will participate in all pair driving, and total of 182 raw data were collected, and data pre-processing and driving safety indicators were driving using R. Driving safety evaluation indicators were selected based on formal car following research, such as acceleration change by interval, we call that acceleration noise, and standard deviation of steering angle speed and deceleration rate to avoid the crash, which we know as drag. This study drives the safety indicators of each section and tries to define where driving safety decreases. Next, we check the driving safety indicator at each section by descriptive statistics. And as the table, color block was emphasized as the average indicator for each driving pair. And blue shows the driving safety is good, and yellow shows the moderate, and red shows the bad. In this table, we showed it as it was confirmed that the driving safety of AV was lower in all evaluation indicators, and it was found that the driving behavior of AV influenced the MV motoring. Mixed pair influenced the MV driving, we known as this yellow block. Then compares the size of indicators based on the rate of change in different sections to the linear of the flat section, which has no change in road alignment, so the driver does not have a lot of driving compression required. So this study calculates the rate change of in different sections to the linear of the flat section. So the section with the largest change rate has the low driving safety, and this table indicates the rank of the safety indicators. And the section with the large rate change is ranked higher. As the conclusion, driving safety of non-signal intersection is low at the longitudinal driving safety indicators. And next, this slide shows the rate of change of the level driving safety index. And it shows that driving safety in driving safety in high in stretch section that do not operate a lot, and it shows that lowest driving safety is the roundabout in the AV pair and mixed pair, and the U-turn section is the in the MV pair. And this slide shows the rate of change of the inter-vehicle safety index by direct, and it shows that all pair is different, and straight ahead at signal intersection, and left turn at non-signal intersection, and U-turn section is the lowest driving safety. Finally, we drive the driving safety vulnerability section with the statistical method by ANOVA and custom analysis. Considering the driving safety of mixed traffic situation, this study intends to present the ANOVA result only for the mixed pair. As a result of the ANOVA, significance probability is less than 0.05. It implies that no hypothesis that the section was the same in the all mixed pairs of the evaluation indicators was rejected. And the results of ANOVA is shown as the table in Right. And the personal analysis shows that the section with the greatest distance from the straight line was selected as the vulnerable area. So we show this red block. I cannot see this red block shows the lowest driving safety, and this blue block is the highest driving safety. Okay. In the next slide, shows the lateral driving safety vulnerability section by the steering wheel speed. It shows that the section with the section with the left turn of signal intersection and roundabout are the biggest difference has, and it shows that these two sections are driving safety of this section is low, and this blue section is low. Next, we show the inter-vehicle driving safety vulnerability section by drag, and this shows that there has no significant change, but it shows that last two sections, which we showed as straight ahead and signal intersection, and left turn and non-signal intersection has the lowest. So, as a result of the analysis, and driving safety of AV pair is the highest in our safety indicators, and the driving safety of the mixed pair, which we call it AB and AV driving together, was safer than the AV pair. So this implies that the introduction of AV can increase the driving safety of the road. And the comparison of the driving safety indicators, AV pair shows the low driving safety at straight ahead section, and MB pair shows low driving safety in U-turn section. In the mixed pair, driving safety was low in the crosswalk and left turn in the non-signal section. And lateral evaluation index shows that the driving safety was low in the roundabout and U-turn section, which has an on-curb section, and driving tests were more difficult. And as the result of the POSOC analysis, the intersection was the analysis of the most vulnerable area in the case of the mixed pair. This because the stop line in the front of the intersection is a point where rapid acceleration and deceleration occurs, and the distance between vehicles are rapidly closer. In addition, it is expected that the derivation process used to identify variable areas of drive safety can be used in other studies related to effectiveness assessment of driving safety and improvement measures. Based on the analysis indicators used in the result of this study, autonomous driving risk intervals and related measures can be prepared according to the actual urban road structure. The driving safety score of each section can be granted by dividing level of changing rate, and the safety evaluation can be performed by adding the section passed in the area where the actual autonomous vehicle is in operation. So in future research, the safety analysis of transportation through traffic simulation can be performed. And in addition, road structure that have not been implemented due to the limitation of the simulation will be tested using a modeling program which will enable driving safety evaluation for complex road structures. And this study was selected for the Best Young Researcher Paper Award in Transportation Research Board And the transportation research record, this paper is currently on the review. And this is my presentation, and thank you for listening.
수고하셨습니다. 저희 잠깐 마지막으로 좀만 쉬었다 할게요. 그래서 지금 43분이니까 5시에 이제 패널 디스커션 하고 마무리하겠습니다. 5시에 다시 시작할게요. 이제 시간이 됐으니 마지막 패널 디스커션을 해보겠습니다. 그래서 이제 한 분 한 분 좀 더 소개를 드릴 텐데요. 한 번만 더 박수를 좀 부탁드릴게요. 먼저 철도기술연구원의 저희 동문이세요. 손승호 박사님 모셨습니다. 저희 교통원료공학과 학과장이신 서원호 교수님 모셨고요. 오늘 UCF의 모하메드 압델라티 교수님이십니다. 마지막으로 카이스트의 니콜 첸 교수님이십니다. 그래서 어떻게 할 거냐면은 이 분들한테 저희가 코멘트를 좀 받을 거고 또 질문을 좀 자유롭게 할 수 있는 시간을 할 거예요. 그래서 일단 먼저 한 분 한 분 코멘트를 좀 받겠고 아마 앞뒤 교수님 말고 여기 손승호 박사님이랑 서원호 교수님이랑 닥터 첸한테 코멘트를 좀 받아보겠습니다. 먼저 손승호 박사님부터. 네, 안녕하십니까. 한국철도기술연구원 미래교통물리연구소에서 근무하고 있는 손승호라고 합니다. 제가 작년에 박준영 교수님 밑에서 박사 학위를 받고 지금 철도기술연구원에서 근무하게 됐는데 또 오늘 이렇게 좋은 자리에 초대해 주셔서 너무 감사의 말씀을 드립니다. 그리고 앞서 진행해 주신 발표들을 너무 잘 들었고요. 지금 당장은 제가 물류 쪽 일을 하고 있다 보니까 물류 쪽 연구를 담당하고 있다 보니까 과거에 제가 박사과정 때 열심히 들었던 유사한 연구의 주제들로 세계적인 석학 교수님과 박사님들의 연구를 너무 재밌게 들어서 오랜만에 예전 생각도 많이 하고 또 배우는 시간이었다고 생각을 합니다. 특별하게 코멘트는 제가 드릴 거는 딱히 없을 것 같고 교수님들 의견 잘 듣고 저도 공부하는 시간을 가지면 좋을 것 같습니다. 네, 이상입니다.
I really enjoy the presentations, and then I don't have a specific comments, but I'm very impressed with all the research work, and then I have a couple of questions for you. First, you propose using the cameras, CCTVs for other purposes, like for other public sector cameras to identify near misses. Right, I understand it's a brilliant idea, and then I think it's beneficial for the society. But I'm just wondering that ideally, you want to have like a bird's eye view camera to identify the near misses. But most of the cameras for other purposes are like very close to the ground, and then you have occlusions and then different angles. So do you have any limitations to figure it out, mitigate the limitations, or any suggestions?
That's a very good question, and that's why when I presented two separate systems. You are right. I mean, it's easier to look at the bird's eye. But actually, most of the current systems in practice or in private sector are roadside and are dedicated cameras. And usually, a large intersection would be covered by actually 4 cameras. But for CCTV, the government will not put more than 1 camera in the intersection, right? And then they rotate it, which create a problem, right? Because it moves. And usually in a traffic management center, they will move it and leave it until they want to look at something else. They will not return it to a predefined location. And sometimes they zoom in and leave it zoomed in, so you cannot see that. So CCTV cameras have their own challenges, and they are not usually high resolution. So they're not the ideal. And as you said, they have the occlusion problem. So there is a distortion in the picture that you need to bring back the images, which is 3D, back into 2D, and then into 3D again, in order to be able to see what is going on. So, so I totally agree with you. And some of the work that we are doing now is actually to match, if we have the same location and we fly the drone and we have the CCTV, and then we match them together. And therefore, maybe you can then calibrate the roadside camera. So anyway, so your question is very decent, and I don't have a very intelligent solution to which way we go. We selected the UAVs because indeed they're easy. But again, their constraint is that they are not continuous, right? Because the battery is unlimited, you know, it's like 20 minutes or 25 minutes and you have to bring it down. But the CCTV camera can work 24 hours. So I think the solution, just to sum all this, the solution is, if we know there is a problem, I think we can fly the drone and identify the problem. But if you want continuous monitoring, it has to be roadside. And maybe the most critical locations, we can have the 4-camera approach, which are dedicated cameras. And the less important, we can have the CCTV. So a combination.
Thank you for your comments. I really appreciate your response. And my second question is, you mentioned it's a brilliant idea to bring the 3 drones and then connect to each other and then tracking all the vehicles. And then I think it's very useful, but you can get a lot out of it. And then you mentioned the calibrating the traffic flow by itself from the images from drone. So I was wondering, can you make a traffic flow theory out of the images from drone? We are just relying when we use the traffic simulation like a Sumo or a Vissim, we use their own inside the Kaplan theory. But if it's like a machine learning system, we know we learn everything from the current images, and then can you build the traffic simulation model out of it? Okay, that will be wonderful. And then my last question is, do you happen to see any significant difference between like a vehicle detection from the daylight and the nighttime?
Okay, so that's again a good question. First, you're not allowed to fly the drone at night or under bad weather. So that rules the drone out. But indeed, of course, particularly when you don't have good street light, then the camera option becomes a problem, right? Because the camera depends on good lighting. So there are infrared cameras that we can use, and then we can use the same approach. But of course, this will be more expensive, right? So these are not, again, the default cameras. What we try to do also is to fuse sensors, to use the LiDAR and camera at the same time. And then at night, you depend more on the LiDAR. So there are other solutions when you use other sensors, like when I talked about the UWB, for example. You can use the UWB once and calibrate the roadside camera, and then you don't need to use the UWB again. Like, for example, want to study pedestrians, right? So you need some pedestrians to cross the intersection, and as long as the camera is at the same angle, same height, and will not move, then you can fuse the UWB and the camera. And then afterwards, you use only the camera, but you adjust it using the UWB. You understand what I'm saying? So the camera from the side will be distorted because there is a closer side, there is a farther side, right? So here you can see maybe the pedestrian and the vehicle clearer, but in the opposite corner of the intersection, the vehicle will be distorted, right? And the trajectory of the pedestrian will change based on the distance and the angle. But if you use one time to calibrate using the UWB, then afterwards you adjust the camera all the time with a fixed amount as long as the camera is present, right? So there are a lot of, I mean, this is again a developing field and how to use multiple sensors, etc. But I want to go back to the issue of calibrating a micro simulation. And actually, we are doing that because there are so many. I mean, the default coefficients in a car following model or lane changing model in, say, VSAM or whatever is still limited, right? And still, when you go to other countries or other travel behavior, etc., you need to calibrate and validate, etc. And you don't have all the situations, right? Because the car following changes in a connected vehicle environment, or when you have a mix of connected and autonomous, or when you have rain, or when you have fog, or I mean, there is unlimited situations that the micro simulation will not cover. And that's why actually, although of course we don't cover fog, etc., because we don't fly the drone, I mean the trajectories that I showed and I said it's an open data set. You notice that I said that the car companies are interested in this data, not only the researchers, because actually when you develop an autonomous car algorithm for car following or lane changing or whatever, you have to start from the human behavior and then optimize it or adjust it so that it becomes more safe for an autonomous car. Right? So they need our trajectories in order to first study and understand the different situations. And then from there, they develop an autonomous car.
Thank you for your wonderful insights. Thank you.
Sounds good.
Yeah.
Thank you, sir. So, Dr. Chen, any comment or question?
Okay. Thank you for inviting me here. I'm Nicole Chen from the Graduate School of Mobility in CAST. So my research topic is related to traffic safety and human factors. So of course now many scholars are focusing on the topics of autonomous vehicle, and because they are expected to reduce the crash rates or injury risk. But the problem is that when you introduce new technologies that offers safety benefits, it usually introduces new risks. So in addition to the technological limitations, autonomous vehicle actually faces human factor challenges. And we all acknowledge that the current ecosystem is not prepared or not ready for the human factor challenges in the future mobility system. So of course, now the technological side is more predominant compared to the human factor side, but insufficient awareness of the human factor challenges will introduce like new risks, as I mentioned, and we need to take care of the human factor issues related to the vehicle automation and the connected environment. So I believe that the PhD student there is doing very fantastic work. So my suggestion to him is that because he's doing something like safe interaction between the autonomous vehicle and the human-driven vehicle, right? So because in the future we will expect a prolonged period of the transition period with actually 3 types of vehicle, which is the autonomous vehicle, human-driven vehicle, and the connected human-driven vehicle. So maybe in his experiment he can ask one user is actually the human driver, but receiving some information from the surrounding traffic, like infrastructure. So I believe it will like enhance his work. And so I would like to ask Professor Adi about the human factor challenges he or his team recognize in their research, because he actually shared the topics regarding the pedestrian safety, right? And actually, I have another question for Professor Ati. It's related to the data. So as the scholars in traffic safety, we used to look at the crash data set. We look at the historical crash data, and then we do the data analysis, which belongs to the reactive safety management. But now we start we all start to look at the proactive safety management. So usually we need to look at the traffic conflict, but so regarding the traffic conflict, we use the connected vehicle data or the CCTV and drone-based trajectories. So what are the pros and cons of this data, using this data? Because actually connected vehicle data maybe will be more popular. I'm not sure, because we expect that the penetration rate of the connected vehicle will increase, right? So, and they are like pro vehicle moving around under different scenarios and different traffic conditions. So maybe they can collect more like various data like compared to other data sets.
I was hoping not to get difficult questions. I'm starting to get a little bit sleepy, but so going back to your first point, just to complicate a little bit what you said about you are totally. I'm not answering yet your question. I'm just commenting on something you said. So I agree that the period we are in is the most complex, right? Because it's the transition period. So it's not only connected and autonomous and human-driven or human with connected. Now, consider that the autonomous or automated, before even we go to autonomous, there are different levels. So the transition will be a mess, right? Because you have, you know, percentage of vehicle level 2 and percentage level 5 and percentage level 4. And level 3 was connectivity, and level 3 without connectivity, and only human. So really the transition is a lot of different combination of things, and that makes it very, very challenging actually. So going back to your questions about the data, all right. So the condition to use conflicts or near misses, number one, that we can measure it. And number two, that we can prove that it is related to crash. So if we know, and there are a lot of research, right? And actually, there are a lot of conflict measures. I mean, we typically use the TTC and the PET, but really there are so many. I mean, you can use acceleration as a parameter, or deceleration, or you can use different calculations of TTC, like MTTC, etc. And there is a whole book by Andrew Tarko, that is about conflicts. So it is more complex than what I mentioned, like two measures, TTC and PET, etc. So if we believe that the conflicts are correlated with crashes, then it's okay to study conflicts, right? And then one of the things that we also have been looking at is, okay, so what is the critical cutoff point? Most of the literature use like 2.5 seconds. So if the say the PET, you know what's the PET, right? So two vehicles pass a certain point, but between them is 2 seconds, then this is a problem. Like 1 second, you just missed each other. 5 seconds, it's not a problem because there's a lot of time. Right? So what is the cutoff point that we consider this a conflict or this is not a conflict? And then other researchers have actually started to say severe conflict, minor conflict, no conflict, right? So I mean, there are a lot of options to look at the conflicts. But again, I think that the concept is, are we okay to continue to look at crashes as our measure or only measure of safety, evaluation, and modeling and analysis, or are we ready to use other measures? And probably the answer is a combination for the time being, until we are comfortable enough to use other measures. And what helps us is that we have the type of data that we are talking about is the more microscopic data, whether we are getting it from sensors or from cameras, etc., etc. So this allows. Actually, what I didn't talk about today is the WAGEO data that I mentioned at the beginning. We have been using WAGEO data actually to determine conflicts. So this is kind of a connected data or a vehicle-specific data, not videos, but data coming from the vehicles that we are using to determine conflicts. So there are a lot of things going on and a lot of combinations that I think we can benefit from. But again, the challenge is what I mentioned is that we have a lot of data, a lot of options. Okay, so what are we going to do, right? To solve a lot of problems. But definitely we are moving away from the traditional transportation. Things like using, total crashes. And we know that the crash database is not perfect. And we know that it's mostly not complete, particularly in the less severe crashes. Okay, how about ADT? Most safety models still use ADT, average daily traffic. Are we serious? I mean, in the 21st century, when we have like trajectories and vehicle-based data, we're still using the average per day? What does this mean? I mean, there are a lot of changes that we need. Believe me, I've been for 20 years criticizing using ADT. And particularly at TRB, like when I go to the safety, they look at me, this crazy guy. I mean, this is 10 years before the Highway Safety Manual was published, which was the major achievement in safety. Still use the ADT and the total crashes. What does this mean? I mean, we prove in recent projects that when you use the ADT and identify the hotspots using network screening, and then when you use more microscopic models like hourly models, like peak hour model or night model, the results are totally different. So the ADT is giving us the wrong results, telling here is a problem. While if you use more microscopic models, maybe here is a problem only at certain times, certain situation, but mostly here is the problem. So actually there is a lot of changes that we have to adapt quickly. And the last thing that I want to tell you, I'm sorry, I talk a lot. Professors talk a lot, right? It's an hour, so we have to fill the hour with talking, right? So you bring a good point about human factors. Really, it's a combination, and we all need to work together. The engineers, the human factors psychologists, or human factors engineers, or the electrical engineers that do the sensors and the connected vehicles, or the computer scientists that do the software, or the policy people. We have to work together and understand each other. So far, mostly, it's improving a little bit, but mostly we think, so I'm a transportation engineer, I think I'm the most important. And the others are, not that important. But when you talk now to the electrical engineers that are doing connected vehicles, they think they are the most important. They don't even want to talk to us. And I mean, you are designing, computer scientists or electrical engineers, you are designing a vehicle that can operate by itself. Is it gonna, operate in an empty space, or is it gonna operate on a roadway that we transportation design, in a traffic that we analyze, going through signals that we transportation design? We don't know that. So at the end, they're going to produce a very sophisticated algorithm, intelligent for a robotic or drug, but it cannot operate in reality because they don't know what we are doing from our side, right? We have to insist to be relevant as transportation/civil engineer, because some others don't believe that we are.
Any more comments? Okay, let's move on to the audience. 혹시 질문 있으신 분 있을까요? 크게 말해주세요. 누구한테?
I have some questions to ask the professor. In former presentation, my name is Shin Park, the third year undergraduate student. And in former presentation, you introduced about the analysis using drones. And in this discussion, you referred some infrared technologies, right? Infrared technologies used.
Infrared.
Yeah.
For cameras at night. Yeah.
If we install some electro-optical and infrared sensors on CCTVs in some important area, I think it will be possible to observe at night or bad weather. What I'm curious about is, if this is possible, which one would be more effective in observation between the compared with the drones or some unmanned aerial vehicles in same places.
As far as I understand your question, right? So I think drone cannot provide continuous observation or coverage. What I was suggesting by drones is flight over specific location to analyze the problem, suggest the solution, make sure that the problem is solved, and move on. It's not a way, although I don't think in the future it could be used for continuous observation in a sense that you have this swarm of drones. I mean, you probably see these shows where you have a lot of drones together with light, right, and they make shapes, etc. So this is a swarm of drones, right? I think there is some research in this direction, not for entertainment, but for using it effectively to survey a location or you know, an area, right? So there is, I think there is future to have drones that can fly longer, you know, better battery. I mean, battery technology in everything comes back, right? So even in our smartphone, the first year you are very happy with the phone, but after the first year, you need to charge it all the time, right? So battery is always a problem. So I think as the technology improves, we're going to have drones that fly longer time. I don't know, maybe use multiple batteries. You know, now military airplanes, they charge in the air, right? So probably there will be time when we do something, like charge the drone in the air or something. But until then, drones specifically to generate trajectories, to be able to analyze traffic. And as Professor Su was saying, it's clear, right? You're looking down, it's very clear, it's two-dimensional. You can see exactly the dimension of the vehicle and therefore identify, you know, certain parameters. Now, this is, of course, you can fly a drone with infrared at night. You can fly a drone with a LiDAR on it. You know, you can do a lot of things, right? But I think that when I mentioned infrared, was that the issue is that the camera technology is great as long as the weather is good and you can see. What you can see with your eyes is what you can see with the camera. If it is raining heavily or it's foggy or it's night, then the camera has a problem. Then you either, if it's clear but night, you can use infrared. Now, suppose a situation when it's heavily raining or fog. Probably you need another type of sensor, such as LiDAR. So I think the solution to very sophisticated, when I arrived Monday night, and even Tuesday morning from Incheon, it was very foggy. And I know there was a very bad accident a few years ago near Incheon because of fog. Right. So this is again one of the typical problems in safety, and we have it in Florida also, is what do you do in fog? How to warn, and this is a perfect example that we need connected vehicles. Really, the solution is connected vehicles. Because in fog, you are driving, you don't see the car ahead of you, which gives you a clue. So you don't even know if the roadway is turning right or left. But if you have infrastructure to vehicle or vehicle to vehicle communication, you know exactly what's coming in, right? You wanted to work a little bit with that. Right?
Yeah, my last project was a full project.
Here, but then you publish this paper for the heads-up display, etc. So anyway, so you have to have another sensor. So I think the solution is redundancy of sensors or fusion of sensors to solve a lot of the issues, because there is no one sensor that is perfect. Did I answer your question?
Yes, thank you for your
혹시 추가 마지막 질문? 네, 마지막 질문 한 명. 크게 말해주세요. 크게.
Sorry for my shortage of English. This is my question to Professor Ati or other panels. Hello, my name is Kim Kyung and I am an undergraduate student majoring in traffic engineering at Hanyang University. I transferred to this major because of my interest in traffic. I'm always striving to solve traffic problems which I'm interested in and complete my assignments to the best of my ability and satisfy my curiosity by exploring new questions during solving my homework. Also, I'm attending courses in Aju University as an exchange student and went to your presentation too yesterday. Thank you. I was impressed by the changes of your field of traffic engineering over the past 5 years, besides your overall 25 years. I believe that we must be proactive in our approach rather than simply following a set path. I'm currently seeking guidance of how to develop the right attitude and engage in meaningful activities as an undergraduate student in this field. Thank you.
Who do you prefer? So let's all take a shot at you. So of course, I commend you that you first you're an undergraduate and you're attending this seminar because it means that you want to know more and learn more. So this is a very good attitude at the beginning of your life. I hope I didn't bore you much because I repeated some of the stuff from yesterday today. So yeah, so you're not bored also. Okay. I tried to change a little bit, but mostly the first presentation was almost the same. So I believe now that the successful engineer would have to be multidisciplinary. So if you are able to take courses from a little bit outside your traditional, so say I'm a civil engineer, right? So if I go out and take some computer science courses or data mining courses or other courses or travel behavior or whatever, human factors or whatever, I think I'll be more comprehensive in my looking at the problem, because the problem, most of the problems now are more complex and need multiple expertise. So I can look at a problem as an engineer, and we have a certain way of analyzing the problem. But it needs also to understand the human side, the policy side, the economic side. I mean, we need to understand a little bit more in order to have a realistic solution. So I think, I don't know how Hanyang allow you to take other courses, maybe a minor, maybe finish your degree and do a master's in smart cities, which will give you a broader. But I think there are people that do an engineering degree and then do MBA, for example. That's a good combination, I think, for people that want a little bit more of administration type jobs. I try to have my students multidisciplinary. Not all my students are civil or transportation. There are computer science, electrical, automotive. And when my students work together as a team, we are able to do more and understand and suggest better solutions. And I learn from them. Like I learned a lot from my computer science students. They taught me a lot. I mean, a lot of what I said today is not a traditional civil engineer, right? But I learned it from my student. And then I gave them ideas and we developed it more. So I guess this would be my advice to you. Just continue to push. Sometimes you need to get a little bit outside your comfort zone and challenge yourself a little bit. And I leave my colleagues also maybe that advice.
Yeah, I totally agree with Professor Ati's suggestions. Myself is like I focus on the multidisciplinary research too. So in addition to traffic thing like transportation engineering, I need to learn about the economics and behavioral science. And yeah, we when we do some research, we need to like apply some theories or some methodologies from other fields. So.
네, 저는 한글로 하겠습니다. 일단은 같은 길을 먼저 걸었던 후배로서 저도 뭐 너무 많은 길이 있기 때문에 그걸 쉽게 누군가가 가르쳐 주지도 않을 거고, 그거를 또 그 길이 맞다라고 아무도 정의할 수가 없어요. 본인의 길은 다 본인이 정하는 것이기 때문에, 그 대신 같은 학교의 선배님들 그리고 교수님들, 그 길을 먼저 걸어온 선배님들은 그 길에 대해서 정답에 가까울 수 있는 좀 방법을 알려주실 분들이 많이 있기 때문에 지금 답을 당장 내릴 수는 없어도 많이 물어보고 경험하고 이런 자리에 참석하셨다는 것 자체부터가 이미 너무 좋은 노력이라고 생각이 들고요. 그렇게 해서 계속 경험을 쌓아가다 보면은 더 좋은 길을 알려줄 수 있는, 좋은 길로 갈 수 있는 확률이 높아진다라고 생각을 하기 때문에 그 길을 계속 찾았으면 좋겠습니다. 네, 감사합니다.
시간이 다 됐으니까 이 정도에서 마무리하는 걸로 하고, Akari, thank you for your four answers, and I'm really honored to have you here right now. Please visit us again.
Invite me.
I'll invite you. 여기서 끝내겠습니다. 감사합니다.